At this very moment, in the vast expanse of the universe, there are more stars than there are grains of sand on every beach on Earth combined. Recent groundbreaking discoveries have illuminated some of the most enigmatic phenomena of the cosmos, phenomena that challenge the very theories upon which our understanding of the universe is built. These findings are sparking new, profound questions about our place in this immense, ever-expanding arena. From the mysterious nature of dark matter and dark energy to the intricate fabric of space-time itself, we are standing at the precipice of a deeper understanding of the cosmos. Join us as we journey into the unknown, exploring the vast stretches of what we do not yet know about the universe we inhabit. Dark matter, one of the most captivating enigmas in cosmology, continues to baffle scientists. Despite making up approximately 27% of the universe, its true nature remains elusive. One of the biggest mysteries revolves around what dark matter is composed of. Several theoretical candidates have been proposed, including weakly interacting massive particles, WIMPs, and axions. Yet, despite extensive research, no definitive evidence has emerged to confirm any of these theories. Another major puzzle lies in how dark matter influences the formation of galaxies. Observations reveal a curious phenomenon. Galaxies rotate at speeds that should cause them to tear apart, yet they remain intact. Dark matter provides a plausible explanation for these dynamics, yet we are still working to understand its full impact. Even more perplexing is why dark matter behaves the way it does. It appears to clump in certain areas, shaping the large-scale structure of the universe, yet remains imperceptible on smaller scales. Scientists are also grappling with the nature of dark matter's interactions with ordinary matter. Most theories suggest that dark matter interacts incredibly weakly with itself and with regular matter, making it exceedingly difficult to detect. Researchers are developing increasingly sophisticated methods to observe these rare interactions, hoping they will lead to breakthroughs that could unlock further mysteries about this elusive substance. An ongoing debate in the scientific community also revolves around dark energy's relationship with dark matter. While dark matter exerts an attractive force, pulling objects together, dark energy seems to have an opposite effect, pushing objects apart. This has led to the accelerated expansion of the universe, raising profound questions about the coexistence and interaction of these two cosmic forces. Understanding how dark matter and dark energy interact is essential for comprehending the overarching dynamics of the universe. Dark energy itself remains one of the most profound and perplexing forces in cosmology. Scientists define dark energy as a mysterious force that permeates all of space, responsible for the accelerating expansion of the universe. Its existence was first proposed in the late 20th century, when observations of distant supernovae revealed a surprising discovery. The expansion of the universe was not slowing down, as had been previously assumed, but speeding up. This unexpected behavior indicated that a new type of energy, distinct from both matter and radiation, was driving galaxies apart. Dark energy is thought to account for about 70% of the universe's total energy density, making it the dominant force in contemporary cosmological models. To probe the nature of dark energy, scientists use a variety of observational tools and techniques. One of the most important methods involves studying supernova, particularly type Ia supernova, which act as standard candles for measuring cosmic distances. By comparing the brightness of these explosions at varying distances, astronomers can track how the universe's expansion is evolving over time. Other key methods include studying galaxy clusters, gravitational lensing, and the cosmic microwave background radiation, all of which provide insights into how dark energy shapes the cosmos. These combined observations are gradually giving scientists a clearer understanding of dark energy's role in the universe. Understanding dark energy is crucial, as it has the potential to change everything we know about the future of the universe. If dark energy continues to dominate, the universe could expand endlessly in a scenario known as the Big Freeze. Alternatively, if dark energy's properties change, other outcomes such as the Big Crunch could unfold. These possibilities force us to confront profound questions about space-time itself, the ultimate fate of celestial bodies, and the very nature of reality. As scientists delve deeper into the mysteries of dark energy through advanced techniques and innovative theories, Each new discovery brings us closer to understanding this enigmatic force. The quest to unlock the secrets of dark energy not only illuminates the forces that have shaped the universe, but also raises tantalizing questions about the fundamental nature of existence itself. Another intriguing cosmic phenomenon is the problem of missing baryons, which refers to a significant discrepancy between the amount of ordinary matter we expect to find in the universe and what we can actually observe. According to our current understanding, baryons, the particles that make up protons and neutrons, account for about 5% of the total energy density of the universe. However, surveys conducted across different wavelengths of light have shown that we can only account for a portion of this expected baryonic matter. The rest appears to be mysteriously missing, leading scientists to question where it might be hiding. One of the most prominent theories is that the missing baryons exist in the vast intergalactic medium, dispersed throughout the space between galaxies in a diffuse, unseen form. Cosmological simulations suggest that these elusive baryons might be in the form of warm or hot gas, spread thinly across the universe. If this is the case, it could significantly alter our understanding of cosmic structure formation and the evolution of the universe itself. The existence of these missing baryons could also indicate that our current models of the universe vastly underestimate the complexity of cosmic processes. The presence of missing baryons might also have profound implications for our understanding of galaxy formation. For instance, the way baryons interact with dark matter during the formation of galaxies might need to be reevaluated. This could lead to a rethinking of how galaxies, like our Milky Way, formed from primordial gas clouds, offering vital clues to the history of our cosmos. As we continue to uncover these hidden mysteries, the potential for new discoveries about the structure and evolution of the universe remains vast. As scientists work tirelessly to unlock the secrets of dark matter, dark energy, and the missing baryons, we are reminded of how much we still do not know about the universe. Each new discovery not only brings us closer to answering some of the biggest questions in cosmology, but also reveals just how much more there is to explore in this boundless and ever-expanding cosmos. The more we learn, the more we realize that the universe's mysteries are far from being solved, and that the journey to understand it is only just beginning. The search for the elusive missing baryons has grown into a significant endeavor, one that bridges the gaps between various domains of astrophysics. Unraveling the mysteries of this missing matter has the potential to illuminate not only the very fabric of cosmic structure, but also offer profound insights into fundamental questions about the nature of matter and energy itself. Thus, the quest for these missing baryons represents a crucial chapter in humanity's pursuit to comprehend the universe's intricate tapestry, revealing the vastness of reality in which we reside. At the heart of our universe lie cosmic voids, immense regions of emptiness that stretch across millions of light years, almost devoid of galaxies compared to other parts of space. These voids are not mere vacuums. They are pivotal to shaping the large-scale structure of the cosmos. These colossal expanses of space play a key role in defining the cosmic web, a vast interconnected structure made of dense clusters of galaxies, which are linked by filaments of dark matter. The voids, acting as the empty spaces between these dense clusters, serve as the gaps in the grand cosmic architecture. Their presence and dynamics help to define the very architecture of the universe. The evolution of the universe is profoundly impacted by the existence and growth of cosmic voids. As the universe continues to expand, these voids are expected to grow larger and more sparse, leading to a decrease in the density of matter within these regions. In turn, the influence of dark energy becomes more pronounced, overwhelming the gravitational forces that dominate in denser regions. The expansion of these voids leads to a distinct alteration in the structural evolution of the surrounding cosmic areas. Galaxies located at the edges of these voids experience unique gravitational forces compared to those nestled in the denser clusters of the universe. This has profound implications for the structure and nature of the galaxies themselves. Interestingly, the very dynamics of these voids influence the formation of galaxies. In the lower density regions of the universe, galaxies tend to form at a later stage than in denser areas. This delayed formation often leads to noticeable differences in the characteristics of these galaxies. Galaxies born within the vast emptiness of cosmic voids are often smaller and have fewer stars, a direct result of the delayed formation and lack of sufficient material to build upon. This presents an intriguing aspect of cosmic evolution, where the voids themselves are far from being passive or empty. They are dynamic regions that influence the very fabric of the universe, shaping its evolution in ways we are still striving to fully understand. Research into cosmic voids has also become a key avenue for investigating the elusive properties of dark matter and dark energy. By studying how voids interact with their surrounding structures, scientists can gather invaluable insights into the mechanics of the universe. These regions act as laboratories where the mysterious forces at play can be observed in their most unfiltered form. This research helps astrophysicists unlock deeper knowledge about the universe's underlying mechanisms, contributing significantly to the broader understanding of cosmic evolution and the fundamental forces shaping the cosmos. In parallel, the Fermi paradox presents an equally profound and compelling challenge to our understanding of extraterrestrial life. Named after the physicist Enrico Fermi, the paradox arises from a stark contradiction. Despite the sheer vastness of the universe and the high probability of Earth-like planets, we have yet to find any concrete evidence of alien civilizations. This gap between expectation and reality compels us to revisit our assumptions about life beyond Earth, spurring deeper exploration into the nature of intelligent life in the cosmos. One striking implication of the Fermi paradox is the possibility that intelligent life may be extraordinarily rare, even in a universe filled with billions of galaxies and countless stars. Despite the seemingly endless number of planets that could potentially harbor life, it is possible that humanity represents one of the very few advanced species. This challenges our assumptions about the conditions necessary for life to evolve into an intelligent form. It suggests that complex life, and particularly intelligent civilizations, may be rare, or perhaps that planetary environments frequently inhibit the emergence of such advanced life. Another intriguing perspective raised by the Fermi paradox is the notion of self-destruction. It is conceivable that civilizations capable of advanced technological development may inevitably create destructive technologies that lead to their own downfall before they can ever explore the stars or communicate with other intelligent beings. This theory presents a sobering reflection on the sustainability of technological progress and the potential risks it poses to the long-term survival of a species. It raises questions about the challenges humanity faces, which could mirror those confronting other advanced civilizations throughout the universe. Moreover, the paradox invites speculation on the possible nature of extraterrestrial civilizations. Perhaps these civilizations are using communication methods beyond our comprehension or are intentionally avoiding contact with us. Some hypotheses even propose that advanced alien societies may have chosen to remain silent, observing us from afar while adhering to a cosmic prime directive of non-interference. These theories add layers of complexity to our ongoing search for life beyond Earth, highlighting the importance of seeking answers in both the vast expanse of space and within ourselves. Adding another layer to the cosmic puzzle is the accelerating expansion of the universe, a discovery that has captivated scientists for decades. This phenomenon was first observed in the late 1990s, when astronomers studying distant supernovae discovered that the light from the farthest supernovae appeared dimmer than expected. This discrepancy suggested that these celestial objects were farther away than previously thought, implying that the universe is expanding at an accelerating rate. This acceleration has been attributed to a mysterious force known as dark energy, which is believed to make up approximately 70% of the total energy content of the universe. Despite its prevalence, dark energy remains a theoretical concept, and its true nature is still unknown. Unlike gravity, which pulls matter together, dark energy seems to exert a repulsive force, counteracting gravity's effects on a galactic scale. This repulsive force causes the accelerated expansion of the universe, causing galaxies to move away from one another at ever-increasing speeds. Alongside the discovery of dark energy, measurements of the cosmic microwave background radiation, the afterglow of the Big Bang, have further solidified the notion of the universe's ongoing expansion and its accelerated nature. This data helps astronomers piece together a clearer picture of the universe's composition and its evolution over time, revealing the interplay of forces shaping the cosmos. The discovery that the universe is expanding at an ever-accelerating rate has sparked numerous questions about its ultimate fate. Will this expansion continue indefinitely, leading to a fragmented, isolated cosmos, or will some other cosmic force intervene, altering the course of this expansion? These questions remain at the forefront of astrophysical research, pushing humanity to further explore the vastness of space in search of answers. As we continue to explore the enigmatic phenomena at the edges of our universe, such as cosmic voids and dark energy, we move closer to understanding the fundamental forces that govern the cosmos. In the end, these paradoxes and mysteries highlight the complexity and wonder of the universe. Far from merely being an empty expanse, the universe is a dynamic, evolving entity with vast regions of voids, accelerating forces, and unsolved enigmas that continue to challenge our understanding of existence itself. Each discovery, while bringing us closer to answers, also raises new questions, ensuring that our exploration of the cosmos will continue for generations to come. The universe is full of mysteries that challenge our understanding of reality, and at the heart of these puzzles lies the cosmic microwave background radiation, CMB. This faint afterglow of the Big Bang offers a snapshot of the early universe, revealing a remarkable uniformity across the entire sky. Yet, hidden within this vast backdrop are tiny fluctuations in density, clues that point to the variations in the early universe. While these fluctuations provide valuable insight into the universe's beginnings, certain anomalies have puzzled researchers for years. Some scientists even argue that these irregularities might suggest the existence of regions that lie beyond our observable universe, or perhaps areas where alternate physical laws could be at play. As we delve deeper into the mysteries of the cosmos, one idea that continues to captivate both scientists and philosophers alike is the concept of the multiverse. The multiverse theory proposes that our universe is not a unique entity, but rather one of many universes, each potentially governed by its own distinct set of laws and constants. This radical hypothesis shakes the very foundations of our traditional understanding of space and time, inviting us to question the nature of reality itself. While still largely speculative, the multiverse theory forces us to confront the limits of our observational tools and the boundaries of our scientific knowledge. It challenges us to consider that the universe we see and study may only be a small part of a much larger, more complex structure. Each of these phenomena, from the cosmic microwave background radiation to the idea of parallel universes, sparks ongoing scientific inquiry. Researchers are relentlessly pushing the boundaries of our knowledge, seeking answers to the fundamental questions about the cosmos. One of the most exciting advancements in this quest is the detection of gravitational waves, ripples in the fabric of space-time caused by massive cosmic events, such as the collision of black holes. These waves travel at the speed of light and carry critical information about the cataclysmic events that produce them. The detection of gravitational waves in 2015 was a landmark moment in the history of astrophysics, confirming predictions made by Albert Einstein's theory of general relativity. Gravitational waves offer a new way to hear the universe, revealing phenomena that were previously invisible to traditional telescopes. When two black holes merge, they send out gravitational waves that can be detected by advanced instruments like the Laser Interferometer Gravitational Wave Observatory, LIGO. By analyzing these waves, scientists can learn a great deal about the properties of the black holes involved, such as their mass, size, and spin, details that were once hidden behind the event horizon, the point beyond which nothing can escape the pull of a black hole. Beyond providing insight into black holes, gravitational waves also deepen our understanding of space-time itself. They serve as direct evidence of how mass influences the curvature of space, a fundamental concept in Einstein's theory of general relativity. The study of these waves prompts further exploration into the nature of black holes and their role in the ongoing evolution of the universe. As we continue to detect more gravitational waves, we anticipate uncovering a wealth of new information not only about black holes, but also about neutron stars and potentially other exotic cosmic events. This burgeoning field of gravitational wave astronomy promises to revolutionize our understanding of the universe, offering a novel perspective on the forces that shape reality. Another recent discovery that has shaken the scientific community is the detection of fast radio bursts, FRBs. These are incredibly brief but intense bursts of radio waves that last only a few milliseconds, but can release energy equivalent to that of the sun over several days. First identified in 2007, these mysterious signals have left researchers puzzled about their origins. Theories range from the collapse of massive stars to more exotic possibilities, such as the collision of black holes or the presence of magnetic neutron stars. Despite extensive observations and technological advancements, the precise cause of these bursts remains elusive. One of the most perplexing aspects of fast radio bursts is their unpredictability. These events occur seemingly at random, and while some are detected as one-off occurrences, only a handful have been observed to repeat. This makes it incredibly difficult to study these bursts in greater detail. Furthermore, the bursts travel across vast distances through the cosmos, and as they do, they interact with the material that fills the universe, altering their properties. Understanding these interactions is crucial because they may provide vital clues about the distribution of matter in the universe, including dark matter, a mysterious substance that makes up a significant portion of the cosmos, but remains largely invisible to current detection methods. The study of fast radio bursts is still in its infancy, but as our technology improves and our observations become more detailed, these bursts could unlock new insights into the violent, energetic processes that shape the universe. Each discovery brings us closer to understanding the fundamental mechanisms that drive the cosmos, making FRBs an invaluable focus of ongoing astronomical research. All of these phenomena point to the fact that the universe is far more complex and mysterious than we ever imagined. Whether it's the faint whispers of the cosmic microwave background radiation, the groundbreaking detection of gravitational waves, or the elusive fast radio bursts, the universe is revealing its secrets bit by bit. And at the heart of all these discoveries is the possibility that our understanding of reality itself may be just the beginning. As we look deeper into the cosmos, we are forced to reconsider what we know about space, time, and the very nature of existence. The multiverse theory, which suggests that our universe is merely one of many, presents a particularly provocative challenge to traditional scientific paradigms. It proposes that every possible outcome of every event might be realized somewhere within this infinite array of universes. This idea opens up new realms of possibility, but it also raises significant questions about the nature of existence. If there are countless other universes, each with its own laws and conditions, then what does this mean for our understanding of reality? How do we reconcile this concept with the scientific method, which relies on observation and experimentation to test theories? Critics argue that if we cannot observe or measure these other universes, then the multiverse theory might be more philosophical speculation than empirical science. Despite these challenges, the idea of the multiverse forces us to confront the limits of our knowledge and pushes the boundaries of scientific thought. It invites us to imagine a reality far beyond what we can see or measure, where the laws of physics may vary and where entire universes exist beyond our comprehension. Whether or not the multiverse theory is eventually proven or disproven, it has already had a profound impact on how we think about the universe and our place within it. Each of these phenomena, whether it's the cosmic microwave background, gravitational waves, fast radio bursts, or the concept of the multiverse, offers a glimpse into the unknown, a glimpse that challenges everything we thought we knew. They fuel our curiosity and inspire a relentless pursuit of knowledge, propelling us toward new discoveries that may one day redefine our understanding of the cosmos. Through these discoveries, we are not only learning about the universe, we are also learning about the very nature of reality itself. The quest for knowledge is far from over, and the universe, in all its complexity, continues to reveal its secrets, one discovery at a time. The concept of the multiverse presents a revolutionary challenge to the singularity of our own universe. It forces us to confront fundamental questions about our existence, probing the very conditions that allow us to inhabit this particular universe. Why are the physical constants we observe so finely tuned, creating the perfect conditions for life to emerge? These questions have long perplexed scientists and philosophers alike, as they delve into the extraordinary precision of the laws that govern the cosmos. The multiverse theory suggests an intriguing possibility. If an infinite number of universes exist, the odds of at least one universe having the right conditions to support life as we know it become far less surprising. This notion reshapes the way we think about the cosmos. Rather than seeing our universe as uniquely suited for life, it positions our reality as just one among many potential outcomes in a larger and more complex multiversal tapestry. However, this theory raises profound philosophical dilemmas that challenge our place in the universe. As we grapple with the implications of the multiverse, the dialogue between cosmology and philosophy becomes ever more critical. Discussions around the multiverse invite deeper contemplation about the very nature of evidence and our definitions of reality. These debates encourage us to question what we can truly know and how we interpret the universe around us. Ultimately, this groundbreaking concept pushes us to rethink our scientific paradigms, urging us to reconsider the fundamental principles that define existence itself. As we continue to uncover more about the cosmos, our pursuit of knowledge becomes a vibrant and continually evolving journey. In recent years, advancements in the field of exoplanet discovery have revolutionized our understanding of which planets might support life. One of the most exciting developments is the discovery of planets that orbit stars within the so-called habitable zone. This zone represents a region where conditions may allow liquid water to exist, an essential ingredient for life as we know it. A particularly notable example is the discovery of Proxima Centauri b, a planet that orbits a star just 2 light-years away from Earth. This proximity allows for more detailed observations of its atmosphere, opening up possibilities for studying its potential to support life. Using high-powered telescopes, astronomers have made fascinating breakthroughs in identifying molecular signatures in the atmospheres of certain exoplanets. Gases such as water vapor, methane, and carbon dioxide have been detected, all of which are key indicators of biological processes. The presence of these molecules, especially when found in environments conducive to habitability, suggests the possibility that life could exist on these distant worlds. These findings not only spark the imagination, but also guide us toward the hope of discovering life beyond our planet. In addition to studying Earth-like planets, astronomers are now exploring the idea of superhabitable worlds. While our current understanding of habitability is based primarily on conditions similar to those of Earth, these researchers propose that there may be planets out there even more suitable for life. Worlds with stable climates, abundant resources, and diverse ecosystems. This shift in perspective opens up exciting new avenues of exploration, encouraging us to imagine what life might look like in environments vastly different from our own. The Kepler Space Telescope and its successors have made immense contributions to this field, cataloging thousands of exoplanets, many of which are similar in size and temperature to Earth. These discoveries spark the hope that we may soon find definitive evidence of extraterrestrial life. One of the most profound developments in recent years has been the discovery of water on Mars. For decades, scientists have debated whether Mars ever had conditions suitable for life. The detection of water, particularly in the form of ice and salty liquid brines, has significantly altered our understanding of the planet's potential to harbor life. Evidence from missions like the Mars Reconnaissance Orbiter has uncovered signs of recurring slope lineae, dark streaks that appear to flow during warmer seasons, likely linked to briny water. These findings suggest that liquid water may still exist in certain Martian environments, raising the possibility that microbial life could have once thrived, or may still exist today. Moreover, the discovery of water on Mars points to the potential existence of a former, more temperate climate, one where life could have emerged and developed. To further investigate this idea, scientists are studying extreme environments on Earth, such as Antarctica and deep-sea hydrothermal vents, where life thrives despite the harsh conditions. These studies offer hope that life could have adapted to the extreme environments of Mars in the past or even survive in the present. As scientists continue to explore the red planet with rovers and landers, they are not only searching for signs of past life, but also studying how water has shaped Martian geology and climate. These evolving findings have propelled Mars to the forefront of our search for extraterrestrial life, positioning it as one of the most intriguing targets in our ongoing quest to find life beyond Earth. At the heart of this cosmic exploration lies the study of the cosmic microwave background, CMB, radiation, an essential remnant from the early universe. This faint glow, which fills the universe, provides a snapshot of the cosmos roughly 380,000 years after the Big Bang. The CMB holds invaluable insights into the structure and evolution of the universe, revealing temperature variations that tell the story of the universe's early density fluctuations, which eventually gave rise to galaxies and larger cosmic structures. In analyzing the CMB, scientists have confirmed the existence of dark matter, which, although invisible, constitutes a significant portion of the universe's mass. Additionally, it has been shown that ordinary matter, the matter that makes up stars, planets, and all known objects, represents only a small fraction of the total mass energy content of the universe. The study of the CMB has also pointed to the existence of dark energy, a mysterious force that is driving the accelerated expansion of the universe. Together, these revelations have reshaped our understanding of cosmic evolution and the fundamental forces that govern it. Perhaps most notably, the CMB has provided a means to estimate the age of the universe, which is now understood to be approximately 13.8 billion years old. This estimate has refined our models of the universe's history, allowing scientists to more accurately trace its origins and development. These measurements not only deepen our understanding of the universe's beginnings, but also highlight the intricate relationship between space, time, and the fundamental forces that shape our reality. As our knowledge expands, the study of these cosmic phenomena continues to challenge and inspire new generations of scientists, philosophers, and dreamers, inviting us all to reimagine the universe and our place within it. The cosmic microwave background, CMB, stands as one of the most compelling pieces of evidence supporting the Big Bang theory, acting as a vital cornerstone in our understanding of the universe's origins. This faint, ubiquitous radiation, which permeates the entire cosmos, has been instrumental in shaping our view of the early universe. What makes the CMB particularly striking is its uniformity, accompanied by only slight fluctuations. These tiny variations align closely with the predictions made by the Big Bang theory, offering further validation for this model as the leading explanation of how the universe came into existence. As scientists continue to refine their observations and measurements of the CMB, particularly with the advent of more advanced technology, we can expect even more profound revelations about the very fabric of the universe. These observations provide a window into the past, allowing us to peer back to an epoch where matter and energy were still in their nascent stages of formation. The CMB, in essence, is a cosmic relic, a snapshot of the universe's infancy, frozen in time. Among the transformative tools in the quest to understand the cosmos is the James Webb Space Telescope, JWST, which has radically altered our comprehension of the universe in ways once considered beyond imagination. Positioned nearly 1 million miles from Earth, the JWST is equipped with cutting-edge infrared technology that enables it to see through the dense cosmic dust and gas that often obscure our view of the universe. This unprecedented ability has allowed astronomers to observe some of the earliest galaxies formed after the Big Bang, galaxies so far removed in time and space that previous telescopes were unable to reach them. These observations have unlocked new insights into the universe's infancy, offering us glimpses of a time that was previously obscured by the limitations of earlier observational technology. Perhaps one of the most groundbreaking achievements of the JWST is its ability to identify and study exoplanets in unparalleled detail. By observing the light that filters through the atmospheres of these distant worlds during a planetary transit, scientists can now detect the chemical makeup of exoplanet atmospheres. This has immense implications for the search for life beyond our solar system. By analyzing these atmospheric compositions, researchers can begin to assess whether these distant planets might harbor conditions suitable for life, or even if they could be home to some form of extraterrestrial life. In addition to its capabilities in exoplanet research, the JWST has provided a wealth of data on the formation of stars and galaxies. It has captured astonishing images of stellar nurseries, regions where stars are born from vast clouds of gas and dust. These observations are reshaping our understanding of how stars come into existence and evolve. By revealing the intricate processes that drive star formation, the JWST is shedding light on the life cycle of galaxies, showing us how galaxies themselves grow and evolve over cosmic timescales. As the data from the JWST continues to accumulate, it has already begun to challenge and refine our theoretical models of the universe. Its ability to look farther back in time than any previous telescope allows researchers to study epochs of the universe that were previously obscured. With each new discovery, we are piecing together an ever clearer, more detailed picture of the cosmos. Our quest for knowledge and understanding of the universe's deepest mysteries has entered an exciting new phase, with the JWST serving as a crucial tool in pushing the boundaries of our cosmic comprehension. In parallel, recent advancements in astrophysics have begun to provide us with a clearer picture of the formation of supermassive black holes, mysterious giants that reside at the centers of galaxies. For many years, scientists debated whether these colossal entities formed from the remnants of massive stars, or whether they grew over time by accumulating gas and other forms of matter. The leading theory today suggests that supermassive black holes may originate from seed black holes. These seeds could have formed in the early universe, possibly from the collapse of extremely massive stars. Over billions of years, these seed black holes would merge and accumulate additional mass, eventually evolving into the supermassive black holes we observe in the centers of galaxies today. Another fascinating theory proposes that supermassive black holes could form through a process known as direct collapse. In this scenario, instead of stars going through the usual stages of evolution, certain dense regions of molecular gas could collapse directly into black holes. This bypasses the intermediate stages of star formation and allows matter to collapse into a black hole relatively quickly, potentially giving rise to the supermassive black holes we see in the universe today. In addition, there is growing interest in the possibility that supermassive black holes might form within the dense cores of stellar clusters. In these regions, stars orbit each other in a highly gravitationally interactive environment. These interactions could result in the formation of a more massive object at the cluster's core. Over time, this object could attract gas and additional stars, gradually growing into a supermassive black hole at the heart of the galaxy. The early universe's environment appears to have played a shaping these black holes, and understanding their formation is critical to unlocking the secrets of galaxy evolution. The timeline of the universe itself offers intriguing insights into the birth of supermassive black holes. Observations suggest that these gigantic black holes began to emerge only a few 100 million years after the Big Bang, raising profound questions about the conditions in the early universe that enabled their rapid formation. As astronomers continue to refine their observational tools, they are delving deeper into the nature of these black holes, exploring not only their origins but also their profound influence on galaxy formation and cosmic evolution. Meanwhile, one of the most enigmatic phenomena in astrophysics is the occurrence of gamma-ray bursts, GRBs, the most powerful explosions in the universe. These extraordinary events are believed to occur during the collapse of massive stars, marking the birth of black holes or neutron stars. However, the precise mechanisms driving these bursts remain elusive. The conventional models of stellar evolution, which predict that massive stars undergo a well-defined process of transformation leading to a supernova explosion, often fail to fully explain the nature of GRBs. Despite their violent and cataclysmic nature, gamma-ray bursts present an extraordinary opportunity for astrophysicists to probe the extreme conditions that exist during the death of stars. These bursts may hold the key to understanding not only the final stages of stellar life, but also the complex processes that govern the transformation of a massive star into a black hole or neutron star. As new theories continue to emerge and observational capabilities improve, gamma-ray bursts remain one of the most fascinating and perplexing phenomena in the universe. They offer a tantalizing glimpse into the most extreme environments and the most intense explosions the cosmos has to offer. However, gamma-ray bursts, GRBs, some of the most powerful explosions in the universe, can release staggering amounts of energy that far surpass what we would typically expect from traditional supernova explosions. This stark discrepancy has raised fundamental questions about the processes taking place inside these dying stars. What is happening in the core of these celestial bodies to produce such immense energy? While our understanding of supernovae is relatively advanced, gamma-ray bursts defy our current models, prompting scientists to investigate what could be responsible for these extraordinary outbursts of power. Observations of both short and long-duration gamma-ray bursts suggest that they might arise from distinct astrophysical processes. Yet, the models that we rely on to explain these events don't fully account for all the variables at play, such as the nature of the host environment, the role of stellar rotation, or the influence of magnetic fields. Moreover, GRBs often occur in unexpected places and under conditions that seem to contradict established astrophysical theories. Some bursts appear to originate from the merger of compact objects, such as neutron stars, rather than the explosion of a single massive star. This revelation forces us to reconsider the various pathways that stellar remnants may follow and how these ultimately culminate in these explosive bursts of energy. This ongoing research continues to evolve with each new observation, acting as a catalyst for revisiting and potentially redefining our understanding of stellar evolution and the explosive final stages of stars. As astronomers gather more data, they find themselves pushed further into uncharted territory, challenging the boundaries of our knowledge about the universe. The quest to understand these cosmic phenomena reminds us of the vast mysteries that still lie ahead, urging us to delve deeper into the heart of the cosmos. In parallel, the exploration of distant exoplanets has opened a new frontier in our understanding of planetary formation and the potential for life beyond Earth. Thanks to advanced telescopes, particularly those equipped with spectrographs, astronomers can now scrutinize the light emitted or absorbed by far-off worlds. By analyzing this light, scientists can determine the composition of exoplanetary atmospheres, identifying the presence of elements such as hydrogen, helium, carbon dioxide, and even water vapor. This information is essential for evaluating the habitability of these distant worlds, helping us understand the fundamental ingredients that may support life. One of the most thrilling discoveries in this field is the detection of chemical signatures that hint at the possibility of biological processes occurring on these planets. For instance, the simultaneous presence of methane and oxygen in the atmospheres of some exoplanets has caught the attention of researchers. On Earth, these gases are often linked to the activities of living organisms, sparking speculation about whether similar biological processes might be occurring elsewhere in the universe. This discovery challenges our assumptions about the prevalence of life and provides tantalizing clues that encourage further investigation into the potential for life beyond our home planet. Beyond the hunt for life, studies of the atmospheric dynamics of distant planets have revealed surprising and sometimes astonishing weather phenomena. Some gas giants, for example, experience extreme winds that reach unimaginable speeds, while others exhibit complex cloud systems that give rise to spectacular weather patterns. These insights not only expand our knowledge of individual exoplanets, but also contribute to a broader understanding of atmospheric science, offering new perspectives on the forces shaping the climates of celestial bodies across the universe. As technology advances, so too does our ability to explore these distant worlds with ever greater precision. The launch of the James Webb Space Telescope, one of the most powerful astronomical instruments ever created, promises to significantly enhance our ability to analyze exoplanetary atmospheres. With its sophisticated instruments, scientists expect to uncover new details about climate trends, seasonal changes, and the potential for ecosystems on exoplanets that lie far beyond our solar system. Each new piece of data adds a layer of understanding, bringing us closer to unraveling the mysteries of the universe and fueling our insatiable curiosity to explore the cosmos. The advancements in technology and observational techniques over the past few decades have dramatically improved our understanding of the universe. Tools like the Hubble Space Telescope have revolutionized our ability to observe distant galaxies, nebulae, and other celestial phenomena, providing unparalleled clarity and detail. These observations have revealed the intricate processes that govern the formation and evolution of cosmic structures, shedding light on the history of the universe itself, stretching back billions of years. Moreover, breakthroughs in detection technologies, such as those capable of detecting radio waves and gravitational waves, have opened entirely new avenues for exploration. The detection of gravitational waves, in particular, has validated predictions made by Albert Einstein over a century ago, and has given us an entirely new way of studying violent cosmic events, like black hole collisions. This innovative capability allows astronomers to probe regions of the universe that are otherwise invisible to traditional optical telescopes, offering us a more comprehensive understanding of the cosmos. Furthermore, the development of advanced computer algorithms and artificial intelligence has enhanced our ability to analyze vast amounts of astronomical data. These tools help researchers detect patterns, anomalies, and relationships in data sets that might otherwise remain hidden, allowing for more refined and accurate interpretations of the universe. As a result, scientists are now able to make sense of millions of celestial objects and phenomena, expanding our understanding of the universe to new heights. The synergy between technological advancements and observational methods has not only enriched our understanding of the universe, but has also sparked new questions and avenues of inquiry. Each discovery leads to a cascade of further questions, driving researchers to probe deeper into the fundamental nature of reality. This relentless pursuit of knowledge has transformed our perception of the cosmos, enhancing our appreciation for the complex and interconnected nature of the universe and our place within it. As technology continues to evolve, so too does our capacity to unlock the mysteries of existence itself. From quantum fluctuations that occurred in the moments following the Big Bang to the most distant reaches of the cosmos, our exploration of the universe continues to reveal its breathtaking intricacy. The study of quantum fluctuations in the early universe, for instance, has provided remarkable insights into the very fabric of reality. These brief, fleeting variations in energy levels likely played a critical role in the formation of the matter and structures we observe today, laying the groundwork for the universe as we know it. In the grand scheme of things, every step forward in our understanding brings us closer to unveiling the mysteries that have baffled humanity for centuries. And as we continue to push the boundaries of what is possible, we realize that we have only scratched the surface of the vast and ever-expanding universe. One of the most profound discoveries in modern cosmology revolves around the intricate relationship between quantum fluctuations and the structure of the universe. These quantum fluctuations, which are essentially tiny, random variations in energy at the smallest scales, are believed to have seeded the initial density variations in the universe. As the universe began to expand after the Big Bang, these tiny, uneven patches of energy began to collapse under the influence of gravitational forces. This process eventually gave rise to the formation of galaxies, clusters of galaxies, and the intricate cosmic web that holds the observable universe together. The idea that galaxies, stars, and planets may have originated from these minute quantum fluctuations is both fascinating and humbling, suggesting that the very fabric of reality is shaped by forces far beyond our direct perception. Studying these fluctuations has also dramatically enhanced our understanding of the cosmic microwave background, CMB radiation, the afterglow of the Big Bang. This faint, ancient radiation serves as a snapshot of the universe when it was just 380,000 years old, offering invaluable insights into its early stages. The patterns and irregularities, known as anisotropies, in this radiation closely match predictions made by the theory of cosmic inflation, a rapid expansion that followed the Big Bang. This connection not only bridges the realm of quantum mechanics with cosmological models, but it also provides a more refined understanding of how the universe evolved. As we peer into the cosmic past, we are uncovering pieces of a puzzle that spans both time and space. Furthermore, investigations into quantum fluctuations have ignited conversations surrounding some of the most enigmatic aspects of the cosmos, namely dark energy and dark matter. These mysterious components, which account for most of the universe's mass and energy, have remained largely elusive. However, the interplay between quantum fluctuations and these invisible forces could hold the key to unlocking some of the universe's most profound secrets. As scientists continue to explore these connections, they not only deepen our understanding of the origins of cosmic structures, but also take us a step closer to revealing deeper truths about the nature of reality itself. The role of advanced astronomical simulations in this field cannot be overstated. With the aid of sophisticated computational models, scientists now have the ability to recreate cosmic events and processes that are simply too vast or distant to observe directly. For example, simulations of galaxy formation and evolution allow researchers to visualize how galaxies collide and merge over the course of billions of years. These simulations reveal the intricate dynamics and structures that shape the universe in ways that are often too complex to capture through direct observation alone. One of the most striking contributions of these simulations is their ability to illustrate the role of dark matter and dark energy in shaping the cosmos. While dark matter does not emit light, it exerts a profound gravitational influence on visible matter, which in turn contributes to the formation of galaxies and galaxy clusters. As researchers adjust parameters and initial conditions in their models, they can simulate how these invisible forces impact the development of the universe's structure. This enables them to test theories that were once speculative, but are now being validated through computational methods. In doing so, these simulations have opened up new avenues of research into phenomena like supernova explosions, black hole formation, and the behavior of neutron stars, key events in the stellar life cycle that contribute to the synthesis of elements. Through the modeling of explosive cosmic events, scientists have made significant strides in understanding the origins of the elements that make up our planet, and indeed, our very bodies. The nuclear processes that occur inside stars, particularly during their explosive deaths as supernovae, are responsible for the creation of many of the elements found in the universe. By simulating these high-energy events, researchers can trace the paths that lead from simple elements like hydrogen to the complex ones that make up life as we know it. These technological advancements have transformed our ability to predict how the universe will evolve in the future, taking into account factors that were once mere theoretical concepts. This growing suite of computational tools not only deepens our understanding of the cosmos, but it also sparks a profound curiosity about our place within it. The interaction between observation and simulation allows scientists to continuously refine their models, testing their hypotheses against the vastness of the universe. In this way, our knowledge of the cosmos is in a constant state of evolution, driven by both technological innovation and the timeless human drive to understand the universe in all its complexity. At the heart of these developments lies the concept of cosmic inflation, a period of rapid, exponential expansion that occurred just moments after the Big Bang. This brief yet transformative event took place approximately 10 to the power of 36 seconds after the universe's birth. The theory of inflation was introduced to address several puzzling observations about the universe's structure, such as its uniformity and flatness. According to the theory, quantum fluctuations in energy levels caused minuscule regions of space to expand at an accelerated rate, stretching the very fabric of reality itself. This rapid expansion effectively stretched space to such an extent that regions of the universe that were once causally connected became separated, leading to the homogeneous and isotropic universe we observe today. Inflation also provides a crucial framework for understanding the distribution of cosmic structures like galaxies and clusters. This is plain. During this inflationary period, tiny quantum fluctuations were magnified, seeding the density variations that would later give rise to the formation of galaxies and larger-scale structures. These small differences in density created the gravitational wells that ultimately drew matter together, forming the vast and awe-inspiring structures that make up the observable universe. In essence, the interplay between quantum fluctuations, cosmic inflation, and the evolution of the universe has transformed our understanding of the cosmos. As we continue to unravel these cosmic mysteries, we inch closer to answering some of the most fundamental questions about the nature of the universe and our place within it. Each discovery serves as both a stepping stone and a reminder of how much more there is to uncover in the vast, ever-expanding expanse of space. The implications of cosmic inflation extend far beyond merely explaining the observable patterns in the universe. This concept suggests that our universe may not be unique, but rather it could be one of many in a vast multiverse. Within this multiverse, other regions could be experiencing entirely different laws of physics, creating a cosmic mosaic of realities. This challenges our long-held understanding of reality itself and raises profound questions about the very nature of existence. If inflation theory holds true, the universe we inhabit could be nothing more than a tiny bubble in a much larger, frothy cosmic foam. Ongoing research into cosmic inflation is not just about peeling back the layers of our universe's origins, but also about advancing our comprehension of fundamental physics. Observations of cosmic microwave background, CMB radiation, provide crucial evidence supporting the inflationary model, offering snapshots of the universe just moments after the Big Bang. These early fluctuations in the CMB hold the key to unraveling the cosmic puzzle. Scientists continue to search for further signs of these primordial ripples, using increasingly sophisticated instruments to probe deeper into the mysteries of the cosmos. Parallel to these investigations, scientists have been grappling with another cosmic mystery: the unexplained movements of certain celestial bodies. Some objects in the universe defy traditional gravitational expectations. These anomalies manifest in unusual orbital patterns, unexpected velocities, and even an apparent lack of visible mass that could account for the gravitational forces at play. Such irregularities have sparked a search for alternative explanations beyond the confines of classical Newtonian physics. One prominent theory that has gained traction is the existence of dark matter. Although invisible and undetectable through conventional means, dark matter is theorized to make up a significant portion of the universe's total mass. Its gravitational influence appears to affect the motion of visible celestial objects. The evidence supporting dark matter comes primarily from the observation of galaxy rotation curves. These curves reveal that galaxies are spinning at speeds that should, in theory, cause them to fly apart. Yet galaxies remain intact, suggesting the presence of unseen mass contributing to their gravitational stability. Another avenue of investigation explores potential modifications to established gravitational theories. Some researchers have proposed adjustments to Einstein's general theory of relativity, speculating that gravity might behave differently on cosmic scales than previously understood. Theories such as modified Newtonian dynamics, M(D), propose that at very low accelerations, the laws of motion could deviate from classical expectations. These modified frameworks aim to explain the anomalous observations, providing a new lens through which to view the cosmos. As technological advancements continue and observational data pours in from telescopes and other instruments, scientists hope to unearth a more complete picture of the forces at play, refining our understanding of gravity and the fundamental laws that govern the universe. This ongoing investigation into cosmic anomalies not only enhances our grasp of gravitational forces, but also sheds light on the intricate tapestry of forces that shape the cosmos. Every new discovery and technological breakthrough brings us one step closer to unraveling the mysteries of the universe. Supernova explosions are among the most awe-inspiring events in the universe, marking the violent death of massive stars. However, despite extensive research, many aspects of these spectacular explosions remain shrouded in mystery. One of the central unknowns is the precise mechanism that triggers these cataclysmic events, especially for Type II supernovae, which result from the collapse of a massive star's core. While the general process of core collapse is understood, the exact conditions that lead to the explosion, such as the influence of rotation and magnetic fields, are still being studied and debated by scientists. Furthermore, there remains considerable uncertainty about the specific sequence of events that transforms the inert, iron-rich core of a dying star into a supernova. While it is known that massive stars undergo fusion processes to create heavier elements until their cores are filled with iron, which cannot produce energy through fusion, the exact chain of events that leads to the core's collapse and subsequent explosion is not fully understood. Theories diverge, and current models heavily rely on computer simulations to replicate these phenomena. However, these simulations have yet to provide a definitive answer, and the exact cause of the supernova explosion remains elusive. The observational evidence adds further complexity to the puzzle. Not all massive stars that appear ready to explode as supernovae do so. Some stars shed their outer layers or lose significant mass before they can ignite the cataclysmic explosion. This mass loss process is poorly understood, raising important questions about how common such scenarios are and what factors ultimately determine whether a star will end its life as a supernova. Astrophysicists are currently utilizing advanced telescopes and simulations to track the precursor activity of these stars more closely. By studying the remnants of past supernova, scientists hope to piece together the puzzle, ultimately revealing more about the conditions that govern these explosions. Through these efforts, we may one day develop a clearer understanding of the forces that shape supernova explosions and, by extension, gain deeper insight into the life cycle of stars and the processes that govern their dramatic ends. Some stars, known as variable stars, exhibit unpredictable flares due to magnetic activity within their atmospheres. These flares can erupt suddenly, releasing vast amounts of energy, often in the form of light and radiation. The phenomenon is particularly prominent in young stars or those with powerful magnetic fields, which suggests that these stars are still in a stage of rapid evolution. These erratic bursts of energy are not just spectacular displays of light, but also pivotal clues that provide insight into a star's development. The underlying mechanisms behind these flares are deeply rooted in the behavior of magnetic fields within the stars. As magnetic energy builds up, the magnetic fields become twisted and tangled. Once the energy reaches a tipping point, it is released in a violent burst, much like a rubber band snapping after being stretched too far. For stars like our own sun, these flares are often linked to sunspots and other forms of surface activity. These flares provide a window into the complex interaction between gravity, radiation, and magnetic forces at work in the star's atmosphere. By observing these stellar flares, astronomers gain valuable insights into the life cycles of stars. Frequent flaring is often seen in younger, hotter stars, indicating that they are still in a period of intense activity. This stage of rapid evolution plays a crucial role in shaping the star's atmosphere, which can, in turn, influence the formation of nearby planets. The erratic flaring behavior seen in these stars is not just a cosmic spectacle. It offers critical clues about the dynamic processes that shape stellar and planetary systems. In conclusion, these energetic bursts are more than just dazzling light shows. They provide vital information about the stages of stellar evolution, shedding light on how stars develop, how they interact with their environments, and ultimately how they influence the broader cosmos. Each flare tells a story, one that deepens our understanding of the forces that govern not only stars, but also the broader cosmic processes that shape the universe. By investigating stellar flares, astronomers are able to extract critical information about the conditions that surround stars. These intense bursts of energy provide valuable insights into the complex activities of a star's magnetic fields and the various processes that govern its life cycle. As stars progress from their early energetic stages into a period of stability, these flares shed light on the forces that shape their evolution and ultimate fate. Meanwhile, another astronomical phenomenon, dark flow, has presented a significant challenge to our understanding of the universe, particularly concerning existing cosmological models. These models are grounded in the framework of the cosmic microwave background, CMB, the faint radiation left over from the Big Bang. Dark flow refers to the strange, unified motion of galaxy clusters that appear to move in a specific direction, one that does not align with expectations based on the theory of the universe's expansion driven by dark energy. Current models, including the widely accepted standard cosmological model, predict that on vast scales, the universe should be isotropic and homogeneous. This means that galaxies should be distributed evenly across the universe and move randomly relative to one another. However, the dark flow phenomenon is at odds with these expectations. It suggests that certain galaxy clusters are not moving randomly, but are instead heading in a distinct direction toward a region near the constellation Leo. This unexpected motion challenges our fundamental understanding of cosmology. If the universe were expanding uniformly, the CMB would appear nearly homogeneous across the entire sky, and such coherent motion on this scale would not be possible. Dark flow suggests that there may be unknown structures or forces at work, extending beyond the observable universe and influencing galactic motion in ways that current models cannot explain. One plausible explanation for this enigmatic movement is the gravitational pull of massive structures that lie beyond the observable universe. These could be enormous superclusters of galaxies or other colossal cosmic bodies exerting their influence on nearby clusters, causing them to deviate from their expected random trajectories. This raises profound questions about the true limits of our observational technology and whether our cosmological models account for all the mass and energy in the universe. If dark flow is confirmed and understood, it could necessitate significant revisions to our theories on the universe's evolution and ultimate fate. The implications of dark flow stretch far beyond this single anomaly. The discovery of such large-scale motion would force a reevaluation of our current understanding of cosmology, potentially giving rise to new physics that could reshape our theories of the universe's composition, structure, and evolution. At the same time, antimatter remains one of the greatest puzzles in modern physics, especially when it comes to the origins of the universe. According to the most widely accepted theories, the Big Bang produced equal amounts of matter and antimatter. However, the universe today is overwhelmingly composed of matter, with antimatter virtually absent. This discrepancy has left scientists scratching their heads and searching for explanations. One of the leading hypotheses to explain this imbalance is the idea of baryogenesis, which suggests that certain conditions in the early universe favored the production of matter over antimatter. In these initial moments, interactions might have resulted in the creation of more baryons, the particles that make up ordinary matter, thus creating a subtle asymmetry between matter and antimatter. Yet the exact mechanisms behind this process remain a mystery, and whether our understanding of fundamental physics is sufficient to explain it is still an open question. The behavior of antimatter itself is also a subject of ongoing research. When antimatter meets matter, they annihilate each other, releasing energy in the form of light and high-energy particles. This annihilation process has been observed in particle accelerators, but no substantial region of antimatter have been found in the observable universe. This absence is puzzling, and it raises the possibility that there may be hidden realms of antimatter, perhaps in remote corners of the universe or in forms that are yet to be discovered. Efforts to detect antimatter are ongoing, both in laboratories and in space. Particle accelerators continue to generate conditions in which antimatter might be produced, while astronomers continue to scan the cosmos for signs of its existence. The detection of antimatter would provide critical insights into the early universe and may offer a deeper understanding of the fundamental processes that shape the cosmos as we know it. In the future, any breakthrough in this field could help solve one of the most profound mysteries in the history of physics. The search for magnetic monopoles, a theoretical concept rooted in the idea that isolated magnetic poles might exist, is another exciting avenue of research in physics. Unlike the dipoles that are commonly found in everyday magnets, magnetic monopoles would be particles with a single magnetic charge, either north or south, rather than both. Theoretical models, particularly those emerging from grand unified theories that seek to combine the fundamental forces of nature, predict that magnetic monopoles should have existed in the early universe. To test this theory, scientists have designed various experiments, including those using particle accelerators and astrophysical observations. Some high-energy particle collisions could potentially produce monopoles, while cosmic rays, fast-moving particles from space, might also provide clues. Although there have been hints of potential monopole signatures, no definitive detection has yet occurred. Still, indirect evidence in the form of materials that display magnetic monopole-like properties offers some intriguing support for their existence. Certain condensed matter systems, for instance, have exhibited topological characteristics that mimic the behavior of magnetic monopoles in a controlled environment. While this does not confirm the existence of true monopoles, it does suggest that the fundamental principles behind them might be observed in novel systems. Researchers remain hopeful, continuing to develop more sensitive detection technologies and refining their theoretical models to increase the likelihood of finding these elusive particles. The pursuit of magnetic monopoles is more than just an intellectual exercise in theoretical physics. Their discovery could shed light on the very structure of the universe itself, revealing new dimensions of our understanding of space-time and the unification of forces. The implications for physics would be enormous, providing new insights into the fundamental laws of nature. Finally, quasars, one of the most fascinating and powerful entities in the universe, continue to baffle scientists despite decades of study. These extremely luminous objects are powered by supermassive black holes at the centers of distant galaxies. Quasars are capable of emitting more energy than entire galaxies, making them some of the brightest objects in the universe. However, despite their brightness, the precise processes that give rise to their immense luminosity remain unclear. One major question revolves around the mechanisms through which matter is funneled into the supermassive black hole. As matter is drawn in, it heats up, producing vast amounts of radiation. However, the details of how this energy is emitted across the electromagnetic spectrum, from radio waves to gamma rays, remain a subject of intense research. Additionally, quasars are known for their remarkable variability in brightness. While they may appear stable over long periods, their brightness can fluctuate over very short timescales, sometimes within a matter of days or weeks. This variability suggests that the regions of emission are incredibly small, possibly as small as the distance between the Earth and the Sun. The cause of this variability and how it relates to the physics of the black hole and the accretion disk surrounding it is still largely a mystery. Unlocking these secrets could offer profound insights into the nature of supermassive black holes and the processes that drive the most energetic phenomena in the universe. Each of these cosmic phenomena, dark flow, antimatter, magnetic monopoles, and quasars, offers a unique glimpse into the workings of the universe at its most fundamental level. The study of these phenomena challenges existing models of cosmology and particle physics, urging scientists to expand their understanding of the cosmos. As technology advances and new discoveries are made, these mysteries may one day be solved, reshaping our view of the universe and our place within it. In the vast and ever-expanding universe, certain phenomena continue to both intrigue and perplex scientists, leading to groundbreaking discoveries and posing profound questions about the fabric of reality itself. Among these phenomena, quasars, distant and incredibly energetic objects, hold a central place in the study of cosmic forces. These powerful entities are not only sources of intense light, but are also observed to eject massive jets of particles that travel at speeds near the speed of light. These jets extend for vast distances into space, creating complex and dynamic interactions with the surrounding intergalactic environment. Despite extensive research, the mechanisms that drive the formation of these jets remain elusive, and their influence on neighboring regions of space is far from fully understood. This gap in knowledge makes quasars not only fascinating subjects of study, but also crucial pieces of the puzzle in our quest to unravel the history and evolution of the universe. The study of cosmic rays, which are high-energy particles traveling through space at nearly the speed of light, adds another layer of complexity to our understanding of the cosmos. These particles, primarily protons, but also including heavier atomic nuclei and electrons, interact with molecules in Earth's atmosphere, creating a cascade of secondary particles. This phenomenon challenges our understanding of high-energy processes in space. Despite decades of research, the origins of cosmic rays remain uncertain. The sources and acceleration mechanisms that propel these particles to such extreme energies continue to evade scientists, sparking debates and fueling curiosity about the true nature of these particles. Cosmic rays offer vital clues about the workings of the universe. Many believe these particles originate from extreme environments, such as supernova explosions, pulsars, and active galactic nuclei, where powerful magnetic fields and shockwaves can accelerate particles to extraordinary speeds. However, the sheer energy of some cosmic rays surpasses what could be expected from these sources alone, prompting researchers to hypothesize that more exotic and potentially more powerful processes are at play. These might include acceleration in the vicinity of black holes or neutron stars, where the forces involved are even more intense. The study of cosmic rays raises profound questions about fundamental physics. The energy of the highest energy cosmic rays challenges existing theories related to particle acceleration and interactions. Observations reveal cosmic rays with energies over 1 billion times greater than those produced by the most powerful human-made particle accelerators, creating a significant gap between what we expect and what we observe. This discrepancy fuels ongoing debates and forces scientists to reconsider our understanding of particle physics, as well as the conditions in the distant universe that could generate such extreme energies. Advancements in technology are aiding scientists in their efforts to track and analyze cosmic rays with increasing precision, allowing them to probe the high-energy processes occurring throughout the universe. As a result, our knowledge of these enigmatic particles continues to expand, shedding light on the fundamental workings of the cosmos itself. The Sun, our closest star, exerts a profound influence on both our solar system and the broader cosmic environment. The Sun's magnetic cycle, which spans roughly 11 years, affects much more than just solar weather. It governs the production of sunspots, solar flares, and coronal mass ejections, each of which has far-reaching implications for space weather and the potential impact on technologies and life on Earth. When the Sun reaches the peak of its magnetic cycle, known as the solar maximum, solar activity intensifies. This surge in activity can disrupt satellites in orbit, interfere with communication systems, and pose significant risks to astronauts in space. During these periods of heightened solar activity, the solar wind, streams of charged particles emitted by the Sun, can create more intense auroras and lead to disturbances in Earth's magnetosphere. These disturbances can affect everything from power grids to navigation systems, demonstrating the intricate relationship between solar dynamics and life on Earth. Furthermore, the Sun's magnetic cycle plays a crucial role in understanding cosmic events beyond our solar system. For example, the increased solar wind during the solar maximum can shield the Earth from cosmic rays to some extent, providing insights into the complex interactions between our Sun and the broader universe. Research into the magnetic cycle of the Sun continues to reveal new mysteries about solar behavior and its effects on the universe around us. By monitoring these cycles, astronomers gain valuable knowledge not only about our own star, but also about similar stars in distant solar systems. This research enriches our understanding of astrophysical processes on a cosmic scale, offering new perspectives on the dynamic and unpredictable nature of our Sun. As we delve deeper into solar phenomena, we uncover essential insights into the workings of the universe itself, offering clues to the broader cosmic tapestry. The concept of space-time curvature, central to Albert Einstein's theory of general relativity, revolutionized our understanding of gravity and how celestial bodies interact. Prior to Einstein, gravity was viewed as a force that acted at a distance. General relativity, however, presented gravity as the warping of the fabric of space-time itself around massive objects. This curvature alters the paths that objects follow, influencing their motion through the universe. When a massive body, such as a planet or a star, is placed in space-time, it creates a depression in this four-dimensional continuum. Other objects, like moons, planets, and even light, follow these curved paths as they move through space-time. The curvature of space-time can be visualized as a marble rolling along a curved surface. The marble naturally follows the curve, and its path becomes predictable based on the degree of curvature. This understanding provides a scientific explanation for why planets orbit stars, or why galaxies interact in certain ways. For example, Earth follows an elliptical orbit around the Sun due to the curvature created by the Sun's immense mass. This interplay of mass and curvature is also responsible for phenomena such as gravitational lensing, where light bends around massive objects like galaxies, revealing the majestic structure of the universe. Space-time curvature not only aids in predicting the movement of celestial bodies, but also deepens our understanding of the fundamental interplay between mass, energy, and the very structure of the universe. As we continue to explore these concepts, we uncover more about the intricate and dynamic dance of the cosmos, expanding our comprehension of the forces that govern everything, from the smallest particles to the largest cosmic structures. Einstein's theory of general relativity, proposed over a century ago, fundamentally altered how we view gravity and the universe itself. This groundbreaking theory predicted the existence of gravitational waves, ripples in space-time caused by some of the most violent and energetic events in the universe. When massive objects such as black holes or neutron stars collide or orbit one another, they create disturbances in space-time, generating waves that propagate outward at the speed of light. These waves were first predicted in 1915, but their existence remained unproven until 2015, when the LIGO Observatory made the first direct observation of gravitational waves. This confirmation of Einstein's predictions marked a new era in astrophysics. The detection of gravitational waves offers a revolutionary new way to observe the universe. Unlike traditional optical telescopes, which rely on visible light, gravitational wave observatories allow scientists to study phenomena that were previously invisible, such as black hole mergers and neutron star collisions. This new method of observation opens up fresh avenues for understanding the universe's life cycle and the forces that shape its evolution. Gravitational waves also have the potential to provide insights into the early moments of the universe, helping to answer fundamental questions about the origins of matter and the forces that govern the cosmos. Each detection of gravitational waves not only confirms Einstein's theory, but also invites us to rethink our place in the universe. As we delve deeper into this new frontier of astrophysics, we are reminded of the vastness and complexity of the cosmos, an ever-evolving mystery that continues to captivate and inspire curiosity in equal measure. One of the most mysterious and fascinating objects in the universe are black holes. These enigmatic regions of space, where gravity is so intense that not even light can escape, remain some of the most intriguing and least understood phenomena in astrophysics. While much has been learned about their properties and behavior, many questions about their true nature remain unanswered. Black holes continue to challenge our understanding of space, time, and the fundamental forces of the universe, making them a subject of intense research and speculation. One of the most pressing and intriguing questions in modern astrophysics centers on the singularity at the core of a black hole. This mysterious point, believed to harbor infinite gravity, challenges our fundamental understanding of the laws of physics. Current theories suggest that in the vicinity of the singularity, gravity becomes so intense that it overwhelms all known forces and causes our understanding of physics to break down. In this region, the familiar laws of general relativity and quantum mechanics, which are central to our understanding of the universe, cease to provide a consistent description of reality. The situation creates an apparent paradox. On the one hand, general relativity describes large-scale phenomena like gravity and space-time curvature, while quantum mechanics governs the tiny subatomic realm. These two theories are known to conflict when applied to black holes, but their collision has yet to be resolved, leaving us in the dark about what truly happens inside this cosmic enigma. Equally perplexing is the so-called information paradox. Quantum mechanics dictates that information about matter cannot be destroyed, yet when matter falls into a black hole, it seems to vanish entirely. The information, which should remain encoded in the universe forever, is lost once it crosses the event horizon, the point beyond which nothing can escape the black hole's gravitational grip. This raises a critical question. Where does all the information go? The dilemma has given rise to numerous competing theories, with one particularly compelling idea suggesting that information might be stored or encoded at the event horizon itself. Yet, despite years of debate, no consensus has been reached. The information paradox, in many ways, remains one of the most profound and unresolved mysteries in modern physics. Moreover, our understanding of black holes is far from complete when it comes to the different types and processes behind their formation. While we are familiar with stellar black holes, those that form from the collapse of massive stars and supermassive black holes, which lurk at the centers of galaxies, the precise mechanisms that create these cosmic giants are still not fully understood. We have only begun to scratch the surface in terms of how black holes influence the evolution of galaxies, the pathways that lead to their formation, and their potential relationship with dark matter. These are crucial questions that continue to drive much of the research in the field of cosmology, and we are just beginning to comprehend the true significance of black holes within the broader structure of the universe. The dynamics of black hole mergers, violent cosmic events that release enormous amounts of energy, add another layer of complexity to our understanding of the cosmos. When black holes collide, they produce ripples in the fabric of space-time known as gravitational waves. These ripples, which travel across the universe, were first directly detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO, marking a breakthrough in astrophysical research. Since then, we've learned much, but key questions remain unanswered. How often do such mergers occur? What can we learn from their frequency and the patterns they leave in space-time about the fundamental structure of the universe? The study of gravitational waves has revealed much about the violent, high-energy interactions in the universe, yet it is still a relatively young field with many mysteries yet to be uncovered. These questions are not just vital to understanding black holes, but they also hold the potential to expand our knowledge of the very fabric of space-time and the origins of the universe itself. Scientists are now using a combination of advanced observational tools and theoretical models to explore how massive celestial bodies, like black holes and neutron stars, warp space-time. These objects create gravitational fields so intense that they bend and twist the very fabric of the universe itself. Einstein's theory of general relativity, which describes how mass influences space-time, comes to life when these extreme objects are observed. By studying how light and other forms of radiation interact with these gravitational fields, scientists can gather critical data on the curvature of space and how it is distorted in the presence of such massive entities. For example, when light from distant stars passes near a black hole, the intense gravity can bend and distort the light's path, a phenomenon known as gravitational lensing. By studying the way light is bent and reshaped, astronomers can infer the mass of the black hole and the degree to which it warps space-time around it. The advent of powerful space-based telescopes and observatories has made it possible to detect these tiny but significant changes in light behavior, offering a direct glimpse into the unseen forces at work in the cosmos. Another critical method for studying the universe's extreme conditions is the analysis of gravitational waves. Cosmic events such as black hole mergers send ripples through space-time, traveling vast distances and carrying with them a wealth of information. By using observatories like LIGO, scientists can detect and analyze these waves to learn more about the cataclysmic processes behind them. For example, studying how gravitational waves behave can provide insights into the characteristics of the objects involved, the energy released during the collision, and the overall impact on the fabric of spacetime itself. Simulations, too, have become a vital tool in understanding spacetime and its behavior under extreme conditions. Using powerful supercomputers, researchers are able to simulate the interactions of massive objects like black holes and neutron stars, modeling the resulting distortions in spacetime. These simulations help scientists visualize phenomena that are incredibly difficult to observe directly, providing a deeper understanding of the complexities of the universe. From this computational work, researchers can make predictions about how spacetime behaves during high-energy astrophysical events and refine their theories of how the universe functions on the grandest scale. Recent advancements have also brought us closer to understanding more exotic phenomena, such as wormholes. Once purely theoretical, wormholes are now the subject of serious scientific inquiry, with some researchers suggesting that they could exist in reality. These hypothetical structures, which are essentially shortcuts through spacetime, might allow for travel between distant points in the universe. The concept of traversable wormholes that are stable enough to allow for safe travel, has gained particular attention. These structures could potentially serve as cosmic shortcuts, making interstellar travel more feasible, and some physicists even speculate that they could offer a method for time travel. However, wormholes remain speculative, and significant challenges stand in the way of proving their existence. The primary hurdle is the requirement for exotic matter with negative energy density, that would be needed to keep a wormhole open. Unfortunately, such matter has never been observed in nature, and no viable way has been discovered to create or harness it. Despite these challenges, the possibility of wormholes continues to spark imagination and fuel scientific curiosity, especially with regard to the potential implications for space exploration and our understanding of the universe. In parallel with the exploration of wormholes, researchers are delving deeper into the relationship between quantum entanglement and space-time. Quantum entanglement refers to a phenomenon where particles become linked in such a way that the state of one particle instantaneously influences the state of another, no matter how far apart they are. Some theorists propose that wormholes might actually be a physical manifestation of this entanglement, providing a potential bridge between distant points in the universe. This idea is still highly speculative, but it represents a fascinating intersection between quantum mechanics and general relativity, two realms of physics that have traditionally been at odds with each other. While the theoretical work continues, the practical challenges of proving the existence of traversable wormholes or applying them to real-world scenarios remain daunting. Still, the prospect of breakthroughs in this area has made the study of wormholes one of the most exciting frontiers in modern physics. As our understanding of space-time deepens, we are also gaining a more nuanced view of time itself. Time dilation, one of the more mind-bending consequences of Einstein's theories, remains central to our understanding of the passage of time in the universe. This phenomenon arises in two key areas of physics: special relativity and general relativity. According to special relativity, time passes at different rates depending on the relative velocity of two observers. As an object approaches the speed of light, its clock will tick more slowly compared to an observer who is stationary. In practical terms, this means astronauts traveling at near light speeds would age more slowly than people remaining on Earth. Similarly, general relativity introduces another form of time dilation, where gravity plays a central role. The stronger the gravitational field, the slower time moves. This has been confirmed through experiments that involve placing atomic clocks at different altitudes. A clock located near a massive object, such as a planet or a black hole, ticks more slowly compared to one situated farther away. These effects, although subtle, have far-reaching implications for our understanding of the universe. Time dilation also has profound consequences for the way we observe distant events. If light from a distant star takes millions of years to reach us, the events we see have already occurred long before the light arrives. This means that the supernova explosion we observe, for example, may have happened millions of years ago, with no way to directly correlate its occurrence to our current timeline. The effects of time dilation challenge our perception of cosmic events and offer a deeper understanding of how time itself behaves in the universe. Time dilation, one of the most profound and mind-bending consequences of Einstein's theory of relativity, raises fascinating questions about the way we perceive time, especially when considering space travel and the exploration of distant galaxies. Imagine, for instance, a spacecraft traveling at speeds approaching the speed of light. For the crew aboard, time would seem to slow down dramatically compared to what is experienced on Earth. What seems like a few years for the astronauts could amount to centuries or even millennia on Earth. This paradox opens up a host of intriguing possibilities, including the notion that astronauts traveling at relativistic speeds might return to a world vastly altered from the one they left, essentially traveling forward in time. This not only challenges our conventional understanding of time, but also highlights the profound relationship between time, motion, and gravity as fundamental forces shaping our perception of the universe. The theory of relativity redefines our understanding of simultaneity, the idea that events that appear to occur at the same time for one observer may not be simultaneous for another, depending on their relative motion. Traditionally, we assume that if two events occur simultaneously, they do so for everyone, everywhere, regardless of where they are or how they are moving. However, relativity reveals that simultaneity is relative. It depends on the observer's frame of reference. As objects move at high speeds, particularly those nearing the speed of light, time behaves in drastically different ways for different observers. For instance, two events that appear simultaneous to one observer may appear as occurring at different times to another observer who is in motion relative to the first. This effect becomes even more pronounced when considering the vast distances and high velocities of objects in the cosmos. For example, when light from a distant supernova reaches Earth, it carries with it information that has traveled through space for millions of years. In a very real sense, what we observe is always a snapshot of the past, filtered through the motion and position of both the light source and the observer. As a result, the concept of simultaneity becomes increasingly complex as we scale our observations to cosmic proportions. In this vast universe, two observers, one on Earth, the other on a distant galaxy, may experience time differently. When they try to synchronize their clocks, they may find that what one considers simultaneous does not align with the other's experience due to their distinct velocities and the effects of gravity. This divergence underscores the fluid and dynamic nature of reality, showing that what one person perceives is not necessarily the same as what another perceives, even when they are supposedly sharing the same moment in time. Relativity challenges us to think of the universe in a new way, not as a static, unchanging backdrop, but as a dynamic, fluid entity where time and space are not merely passive observers, but active participants in the story of the cosmos. As we extend our understanding to galactic events, such as the collision of galaxies or the motion of binary star systems, we begin to appreciate the complexity of how time and space evolve. The more we learn, the more we realize that the fundamental nature of reality is far stranger than our everyday experiences might suggest. The effects of relativity offer a profound reminder that the universe operates on principles that differ radically from our everyday intuitions, urging us to reconsider the very nature of reality itself. Quantum mechanics, a field that operates at the smallest scales of the universe, plays a crucial role in deepening our understanding of space and time. It suggests that the fabric of the universe may not be as continuous as once believed. Instead, emerging theories propose that space-time could possess a discrete nature at the most fundamental scales, possibly altering how we view the universe at its core. One of the most intriguing concepts in quantum mechanics, quantum entanglement, highlights how particles can become mysteriously linked, such that the state of one particle immediately influences the state of another, no matter the distance between them. This phenomenon defies traditional notions of locality, raising profound questions about the very structure of space and time. If particles can influence each other over vast distances in such a manner, could space-time itself be composed of interconnected points rather than being a smooth, continuous fabric? The study of black holes provides another fascinating glimpse into the intersection of quantum mechanics and general relativity. When massive amounts of matter collapse under intense gravitational forces, they create regions of space-time so warped that even light cannot escape. Here, quantum mechanics suggests that information about the matter that falls into a black hole is not lost, even though it is swallowed by the singularity. This leads to what is known as the information paradox, a profound conundrum that challenges our understanding of both quantum mechanics and general relativity. Understanding how information is preserved or lost within black holes is a critical step in unraveling the mysteries of space-time and reality itself. This intersection of quantum mechanics and general relativity has sparked an ongoing quest to develop a unified theory, often called quantum gravity, that can bridge the gap between the incredibly small world of quantum particles and the grand cosmic scale of general relativity. Theories such as string theory and loop quantum gravity propose that the fundamental building blocks of spacetime are not particles, but rather tiny, vibrating strings or discrete loops. These ideas aim to provide a more complete picture of the universe, merging the quantum realm with the cosmic ballet of galaxies and gravitational waves, offering a radically different view of the universe's architecture. One particularly intriguing concept in theoretical physics is that of space-time foam. This hypothesis suggests that at the smallest scales, around the size of the Planck length, space-time itself exhibits a turbulent, frothy structure driven by quantum fluctuations. These minute fluctuations in space-time may have had a crucial role in shaping the early universe. During the first moments after the Big Bang, the universe underwent rapid expansion in an environment of extreme temperatures and densities. It is believed that space-time foam played a pivotal role in this turbulent epoch, providing a dynamic backdrop against which the formation of particles and the distribution of matter occurred. What we perceive today as the smooth fabric of space-time might have once been a chaotic and irregular landscape, fundamentally altering the behavior of the very particles and forces that make up the universe. The concept of space-time foam also connects to theories of quantum gravity, suggesting that our understanding of gravity at quantum scales remains incomplete. If space-time is indeed foamy, this provides a framework for exploring how gravity operates on the smallest scales, with implications not only for understanding black holes, but also for understanding the evolution of the cosmos itself. The quest to understand space-time foam is not just an academic exercise, but a key step in answering some of the most profound questions about the origins and fate of the universe. As scientists continue to explore these early moments of the universe's existence, they are also striving to bridge the gap between quantum theories and classical descriptions of gravity. This search could uncover entirely new insights into the history and future of the universe. Space-time, in all its complexity, continues to capture the imagination of researchers and physicists worldwide. The next generation of experiments and observatories, from particle physics to astrophysics and gravitational wave detection, promises to yield new discoveries that will deepen our understanding of this fundamental concept. Gravitational wave observatories, for example, will enhance our ability to detect the ripples in space-time caused by colossal cosmic events, such as the merging of black holes and neutron stars. By studying these ripples, scientists hope to uncover new aspects of both general relativity and quantum physics. Projects like the Large Hadron Collider continue to push the boundaries of our understanding, probing the fundamental particles of the universe and seeking answers to long-standing mysteries. Meanwhile, advancements in gravitational wave detection, such as the upcoming upgrades to the Laser Interferometer Gravitational Wave Observatory, promise to reveal even more subtle cosmic phenomena, shedding light on time dilation and the intertwining of space and gravity. These future endeavors hold the promise of uncovering profound insights into the nature of space-time and how it shapes the universe. By observing these cosmic phenomena with the latest technological advancements, scientists are on the verge of piecing together a clearer, more comprehensive understanding of the universe's structure, one that challenges our deepest assumptions about the nature of reality, space, and time. In recent years, the exploration of extreme environments in space has become one of the most exciting frontiers of scientific discovery. Missions like the Event Horizon Telescope, which famously captured the first image of a black hole, are not only pushing the limits of technology, but also providing invaluable data that directly tests our understanding of space-time. Such groundbreaking efforts hold the potential to unlock some of the most fundamental questions about the universe. Meanwhile, the pursuit of knowledge about dark matter and dark energy remains equally crucial. These enigmatic forces, which are believed to play a central role in the expansion of the universe, could hold the key to revolutionary insights into the very fabric of space and time. These forces, which continue to baffle scientists, are not just theoretical curiosities, but vital pieces of a cosmic puzzle. The exploration of dark matter and dark energy promises to not only answer some of the most pressing questions about the universe's past, but also raise new ones that will continue to shape the future of astrophysics and cosmology. The classification of celestial objects, such as planets, moons, and other cosmic bodies, has long been a cornerstone of astronomical research. This classification, based on a set of established criteria, helps scientists categorize the diverse range of objects we observe in the cosmos. A planet, for example, is defined as a celestial object that orbits a star, is spherical in shape due to its own gravity, and has cleared its orbital path of debris. This definition, though seemingly straightforward, has evolved as new discoveries challenge our understanding of what constitutes a planet. As our exploration of the solar system and beyond progresses, these definitions continue to adapt. New discoveries regularly prompt scientists to reevaluate old criteria and expand our knowledge of celestial mechanics. Moons, for instance, are natural satellites that orbit planets. While moons vary widely in size and composition, from the massive Ganymede, larger than the planet Mercury, to small, irregularly shaped bodies, their study offers key insights into the history and formation of the planets they orbit. Moons can often reveal secrets about their host planet's gravitational influence and provide crucial information about the conditions that led to their creation. Beyond planets and moons, the term celestial body encompasses a vast range of natural objects in space. This includes not only stars and planets, but also comets, asteroids, and meteoroids. The classification of these objects is constantly evolving, fueled by the wealth of new information provided by powerful telescopes and ambitious space missions. The discovery of numerous objects in the Kuiper Belt and beyond, for example, has reignited debates about what should be considered a planet. This debate led to the reclassification of Pluto as a dwarf planet in 2006, sparking discussions that continue to challenge established norms in the scientific community. As technology advances, our understanding of celestial bodies deepens, highlighting the dynamic nature of astronomical classification. New discoveries often prompt a reassessment of existing definitions, revealing the complexities of the universe and reminding us of how much more there is to learn. The exploration of planets, moons, and other celestial objects is not just about defining what we see, it's about expanding the very boundaries of our understanding. One of the most fascinating aspects of studying stars is determining their ages and understanding the stages of their life cycles. Scientists employ several methods to do this, each tailored to the unique characteristics of the star in question. One of the primary techniques involves analyzing the light emitted by a star. By studying its spectrum, astronomers can determine key properties such as the star's temperature, luminosity, and chemical composition. These properties allow scientists to classify stars on the Hertzsprung-Russell diagram, a crucial tool that correlates a star's brightness and temperature with its evolutionary stage. Another important method involves studying the mass of a star. The mass-luminosity relationship is a key concept here, as more massive stars burn through their fuel more quickly, spending only a few million years in their most luminous phases. In contrast, smaller stars can last for billions of years. By gauging the mass of a star, scientists can estimate its age with a reasonable degree of accuracy. In addition, when stars are in stable phases, such as the main sequence, their mass can offer valuable insights into their age and life history. For stars within specific clusters, such as globular and open clusters, scientists use a method known as stellar populations. This technique involves estimating the age of the cluster as a whole by identifying the most massive stars that have already evolved beyond the main sequence. Since all stars in a cluster are believed to have formed around the same time, this method allows astronomers to estimate the cluster's age, providing a collective view of a group of stars rather than focusing on individual stars. More advanced methods involve examining the abundance of specific elements within stars. As stars age, they synthesize heavier elements through nuclear fusion. By comparing the ratio of heavy elements to light elements in a star's spectrum with theoretical models of stellar nucleosynthesis, scientists can derive more precise age estimates. Through these various techniques, researchers piece together a detailed picture of a star's cycle, from its birth in a nebula to its eventual death as a white dwarf, neutron star, or black hole. Asteroid belts, too, play a fascinating role in our understanding of the solar system. These regions, composed of rocky debris left over from the early stages of planetary formation, offer important clues about the conditions that shaped the planets. The most well-known of these belts is the one located between Mars and Jupiter, where millions of asteroids orbit the Sun. Studying these remnants allows scientists to gain insights into the primordial materials that existed when our solar system was still in its infancy, around 4.6 billion years ago. But asteroid belts are not just valuable for what they can tell us about the past, they also serve as time capsules, preserving the history of our solar system's formation. Each asteroid is like a fragment of a bygone era, offering a glimpse into the composition of the materials present when the planets were first coming together. By analyzing these asteroids, scientists can uncover the processes by which they aggregated and evolved, shedding light on the growth and destruction that occurred during planetary development. One of the most intriguing questions that asteroid belts raise is why some material coalesced into planets, while others remained as smaller bodies. In the case of our own asteroid belt, the gravitational influence of nearby planets, particularly Jupiter, played a key role. Jupiter's immense gravitational pull prevented the asteroids from merging into a larger planet, leaving behind a collection of smaller bodies. This dynamic balance between forces has led to significant research into planetary migration and the variations in planetary systems around other stars. The study of asteroid belts and their role in planetary formation continues to fuel scientific inquiry, offering profound insights into the forces that govern the evolution of planetary systems. As we continue to explore the cosmos, these regions will undoubtedly remain a critical focus of research, helping to reveal more about the processes that shaped our solar system and others like it. The vast asteroid belts, often regarded as remnants of our solar system's formation, hold the potential to reveal groundbreaking insights into the future of space exploration. These cosmic regions, scattered between the orbits of Mars and Jupiter, are far more than barren fields of space debris. They offer a trove of raw materials that could fuel humanity's ambitions to venture beyond Earth. As technology continues to advance, the notion of mining asteroids for metals, water, and other vital resources is becoming not only plausible, but increasingly realistic. The study of these asteroid belts is crucial, not only because it enriches our understanding of the solar system's history, but also because it lays the groundwork for future missions that could take us to distant worlds. Imagine a future where the raw materials needed for space colonization, whether for building infrastructure on other planets or sustaining human life in orbit, are harvested directly from these celestial bodies. Asteroid mining could become a pivotal resource for mankind's ventures beyond Earth. Now, consider the enigmatic neutron stars, one of the most fascinating remnants of stellar death, and their critical role in expanding our understanding of the universe, especially in the study of gravitational waves. Neutron stars come into existence when massive stars, having exhausted their nuclear fuel, can no longer maintain their weight through fusion. This inevitable fate results in a spectacular supernova explosion, which expels the star's outer layers and compresses its core. If the remaining core has a mass between 1.4 and 3 times that of our Sun, gravitational forces force protons and electrons to merge, forming neutrons. The resulting neutron star is incredibly dense, one of the most extreme states of matter in the universe. With diameters of roughly 20 kilometers, these stellar remnants can possess a mass greater than that of our entire Sun. The density is so extreme that a single teaspoon of neutron star material would weigh about 6 billion tons on Earth. The gravity of a neutron star is staggering, more than 2 billion times stronger than Earth's. This intense gravitational force warps the very fabric of space-time around them. Neutron stars also exhibit extraordinary magnetic fields, trillions to quadrillions of times stronger than Earth's own magnetic field, which influences how these stars emit radiation and interact with their environment. Many neutron stars, or pulsars as they are known when they emit beams of radiation, rotate at astonishing speeds. Some pulsars complete hundreds of rotations per second, making them some of the fastest rotating objects in the universe. Their rapidly spinning nature, along with their powerful magnetic fields, creates beams of radio waves that sweep across space like a lighthouse beacon. These beams can be detected from Earth, providing valuable data that help us understand the physics of extreme conditions. Brown dwarfs, often referred to as failed stars, represent a unique and mysterious class of objects that straddle the line between stars and planets. These objects, with masses ranging from 13 to 80 times that of Jupiter, lack the mass necessary to initiate the process of hydrogen fusion, which is the hallmark of true stars. Instead, they generate heat through gravitational contraction and a form of fusion called deuterium fusion, involving the heavier isotope of hydrogen known as deuterium. While brown dwarfs are cooler than traditional stars, with surface temperatures ranging between 1,000 and 2,500 degrees Celsius, they still glow faintly in the infrared spectrum, far less visible than the bright light emitted by more massive stars. This infrared glow makes brown dwarfs harder to detect and study, requiring specialized telescopes capable of observing in the infrared range. The term failed star is a bit of a misnomer, as brown dwarfs play an important role in the cosmic ecosystem. Though they never achieve full stellar status, they occupy an important niche in the evolution of celestial bodies. In fact, the study of brown dwarfs provides insights into the processes that govern star formation and the early stages of planetary formation. Interestingly, brown dwarfs can also have atmospheres rich in complex molecules like methane and water, a characteristic that further distinguishes them from both traditional stars and planets. Their study offers a rare glimpse into the transitional phase between the largest planets and the smallest stars, deepening our understanding of the diverse types of objects that populate the universe. Black holes and neutron stars, both final stages in the life cycles of massive stars, have profound impacts on the universe around them. Neutron stars, with their incredible density and powerful magnetic fields, can draw in material from companion stars, leading to phenomena such as X-ray bursts. In these cases, the matter pulled into the neutron star's intense gravitational field is heated to extreme temperatures, emitting powerful radiation in the form of X-rays. Black holes, on the other hand, exert an even more extreme gravitational pull. The matter that falls into a black hole forms an accretion disk, a swirling mass of gas and dust that heats up and emits X-rays before being swallowed by the singularity at the center. This accretion process is one of the hottest and most energetic phenomena observed in the universe. When black holes and neutron stars collide, they create cataclysmic events that release gravitational waves, ripples in space-time that travel outward across the cosmos. These cosmic collisions not only release enormous bursts of energy, including gamma rays, but they also create heavy elements like gold and platinum, enriching the universe with the materials that make up everything from planets to the jewelry we wear. Observations of these mergers have given scientists crucial data on the nature of these compact objects, but many questions remain about the exact conditions that enable such collisions and what they can tell us about the state of matter at such extreme densities. Supermassive black holes, which reside at the centers of most galaxies, are some of the most mysterious objects in the universe. While their gravitational influence can be detected through the movement of surrounding stars and gas clouds, direct observation of these black holes remains out of reach. They present a paradox in modern physics, where the theory of general relativity, which describes large-scale gravitational phenomena, clashes with the principles of quantum mechanics, which governs the microscopic world. This tension lies at the heart of many unresolved questions about the nature of time, space, and information. One of the most hotly debated topics is what happens to matter and information once it crosses the event horizon of a black hole. Does it get destroyed, or is it somehow preserved? As observational technologies improve, such as gravitational wave detectors and advanced telescopes, we are slowly gaining the tools needed to unravel these profound mysteries. At the grand scale of the universe, galaxies are born from the intricate dance of matter and energy. In the beginning, the universe was a dense, hot sea of particles and radiation. Over billions of years, fluctuations in this primordial soup began to shape the early universe, with areas of higher density attracting more matter through gravity. This led to the formation of the first stars, which in turn grouped together to form the first galaxies. The process of galaxy formation is intimately tied to the large-scale structure of the universe, where the gravitational pull of dark matter formed vast cosmic filaments and clusters that would later become the homes of galaxies. The formation of stars within these early galaxies was a critical step in shaping the universe we observe today. The explosions of massive stars and supernovae enriched the surrounding gas with heavier elements, which allowed for the formation of new stars and planets. Over time, these processes led to the diverse range of galaxy types we see today, from spirals to ellipticals. Despite our understanding of galaxy formation, many questions remain, particularly regarding the role of dark matter. Though its existence is inferred from its gravitational effects, the precise way in which dark matter interacts with normal matter during the formation of galaxies is still not well understood. In the ongoing exploration of the cosmos, each discovery raises new questions, creating a constantly evolving picture of the universe's complexity. The interactions between black holes, neutron stars, brown dwarfs, and galaxies provide us with a deeper understanding of the forces that shape the universe. From the origins of celestial bodies to the death throes of stars, these phenomena serve as cosmic laboratories, helping scientists unravel the mysteries of space, time, and matter. As we continue to explore the cosmos, we are bound to uncover even more astonishing revelations that will forever change our understanding of the universe. The origins of the structures in the early universe, commonly referred to as the cosmic web, remain an unsolved mystery. These intricate patterns, composed of vast voids, filaments of dark matter, and clusters of galaxies, offer an enigmatic glimpse into the formation and evolution of the cosmos. Yet, the precise conditions that led to their creation are still not fully understood. As if that weren't enough to stir our curiosity, another captivating puzzle emerges: the influence of supermassive black holes. These colossal gravitational beasts residing at the hearts of most galaxies have a profound impact on the development of galaxies themselves. Their formation, growth, and the intricate relationship between these black holes and their host galaxies challenge the very foundations of current astrophysical theories. As scientists continue to delve into these phenomena, it's clear that the road ahead is filled with unanswered questions, opening the door for groundbreaking discoveries that could illuminate the mechanisms behind galaxy formation and evolution. An often overlooked yet crucial aspect of our quest to understand the universe's past is the study of cosmic dust. These tiny particles, ranging from carbon-based compounds to silicate minerals, serve as time capsules, witnesses to the cosmic processes that have shaped galaxies, stars, and even life itself. Cosmic dust is produced in the cooling regions of space, frequently by the death throes of stars. As it forms, it retains a record of the elemental composition of the space in which it resides. Every grain of dust carries within it a story, a history of the stellar processes that have unfolded in the universe. By studying this dust, astronomers can begin to piece together the timeline of the universe's chemical evolution. For example, during the formation of stars or the explosive death of a star in a supernova, heavy elements like iron and gold are synthesized and cast into the surrounding interstellar medium. This process enriches the gas and dust in the vicinity, offering scientists vital clues about the origins of the materials that make up new stars, planets, and even life. The very composition of cosmic dust can reveal the identities of long-dead stars, shedding light on the intricate process of material recycling that has been ongoing for billions of years. The interaction between cosmic dust and the light emitted by distant stars further enhances our understanding of its properties. By analyzing how dust absorbs and re-emits light, scientists can infer the temperature, density, and chemical makeup of these particles. This, in turn, helps astronomers understand how galaxies evolve and how early star-forming regions were influenced by the presence of cosmic dust. Moreover, cosmic dust serves as a cosmic archaeologist, revealing conditions in the early universe and offering a glimpse into the formation of the first stars and galaxies. Every speck of dust tells a tale about the intricate web of elemental life that has existed from the universe's very beginning. Through these seemingly tiny particles, we gain insight into the ongoing processes that continue to shape the cosmos today. Equally crucial to our understanding of galactic evolution is the study of star clusters, which provide valuable clues about how galaxies evolve over time. These clusters, groups of stars that share a common origin in a single molecular cloud, act as natural laboratories for astronomers, allowing them to investigate the forces that govern star formation, stellar evolution, and galaxy dynamics. The distinct properties of each cluster, such as its age, chemical composition, and physical structure, act as time capsules, offering a snapshot of the environment in which these stars were born. By analyzing these clusters, scientists can gain insights into the conditions that existed in the early universe and how stars contributed to the chemical enrichment of the galaxy. Star clusters come in two primary forms: open clusters and globular clusters. Open clusters are generally younger, containing fewer stars, and are often dispersed in shape. In contrast, globular clusters are much older, denser, and often contain hundreds of thousands of stars, making them some of the oldest structures in the universe. By examining the properties of these clusters, astronomers can track how the chemical and physical characteristics of galaxies have changed over time. As clusters evolve, they undergo interactions with their surroundings, whether through the formation of new stars or the merging of multiple clusters, providing astronomers with insight into the complex gravitational dynamics within a galaxy, including the elusive influence of dark matter. The study of star clusters, therefore, is not just about understanding the evolution of stars, it's about unraveling the fundamental processes that have shaped the galaxies we observe today. As clusters evolve, they leave behind traces of their history, which, when pieced together, help us understand how galaxies, including our very own Milky Way, have transformed over billions of years. These stellar remnants also serve as markers of the galaxy's gravitational field and mass distribution, offering vital clues about the presence of dark matter and other unseen components that influence galactic dynamics. The study of quasars, those incredibly luminous and distant objects, presents another frontier in our understanding of the universe. These enigmatic cosmic powerhouses are not only bright enough to outshine entire galaxies, but are also among the most distant objects observed in the cosmos. Quasars are powered by supermassive black holes, whose gravitational forces pull in vast amounts of matter from their surroundings. As this matter spirals into the black hole, it forms an accretion disk, a swirling mass of gas and dust, heating up to extreme temperatures and emitting intense radiation across the electromagnetic spectrum, including radio, optical, and X-ray wavelengths. By observing the light emitted or absorbed by quasars, astronomers can deduce crucial information about their composition, velocity, and distance from Earth. The key to understanding quasars lies in the study of the supermassive black holes at their centers. These black holes, with masses ranging from millions to billions of times that of our Sun, generate tremendous gravitational forces that shape their surroundings. As matter is drawn into the black hole, it heats up, releasing vast amounts of energy in the process. By analyzing the light emitted by the accretion disk, scientists can learn about the black hole's properties and activity, unraveling the mysteries of these extraordinary objects. The study of quasars not only deepens our understanding of black holes, but also provides insights into the formation and evolution of galaxies themselves. Quasars represent a stage in the life of a galaxy, one in which the supermassive black hole at its center has become highly active, emitting vast amounts of energy and influencing the surrounding galaxy. As astronomers continue to probe these distant and powerful objects, they bring us closer to unraveling the complex and fascinating story of the universe. In the vast expanse of the cosmos, scientists are continually investigating the enigmatic objects known as quasars, or quares, to understand their profound influence on the universe. These powerful energy sources not only shed light on their own origins, but also serve as essential tools in deciphering the fundamental processes of cosmic evolution. One of the most fascinating aspects of quasars is their interaction with the surrounding intergalactic medium. The intense radiation they emit has the ability to drive gas out of nearby galaxies, affecting critical processes like star formation. This interaction leads to what scientists call feedback, where the energy released by quasars influences the very structure and evolution of galaxies and their surrounding matter. By studying these effects, researchers are piecing together how quasars shape the broader cosmic landscape. In order to understand these complex phenomena, advanced simulations have become indispensable tools. These simulations recreate scenarios where quasars' energetic emissions interact with and transform their surroundings. They help scientists visualize, predict, and explore how quasars not only evolve but also influence the cosmic structures they inhabit. Through this ongoing research, we are unraveling the mysteries of quasars, and in doing so, gaining crucial insights into the formation of galaxies, stars, and the universe as a whole. As scientists dive deeper into the study of quasars, they also encounter a broader puzzle: the large-scale structure of the universe itself. The universe is not a random, disordered place. It exhibits a fascinating, web-like pattern that connects galaxies, galaxy clusters, and cosmic filaments. This intricate structure is often referred to as the cosmic web, and its study raises fundamental questions about the very nature of the cosmos. The cosmic web stretches across immense distances, revealing the deep interconnectedness of galaxies, clusters, and vast voids. It is a manifestation of how gravity has shaped the universe over billions of years, pulling matter together and forming clumps of galaxies. However, this grand design is not random. Galaxies and clusters of galaxies follow the web's filaments, long, thread-like structures composed mainly of dark matter and hydrogen gas. While the voids between these filaments can be hundreds of millions of light years across, mostly devoid of galaxies, the filaments themselves represent the rich, dense regions where galaxies are most concentrated. Understanding the cosmic web is no small feat. Our current cosmological models are based largely on the Big Bang theory and general relativity, which predict that the universe should exhibit a certain degree of uniformity on large scales. Yet observations show that the universe is anything but uniform. There are slight but significant fluctuations in the density of matter, revealing the gravitational effects of dark matter, a mysterious and largely invisible substance that exerts a profound influence on the universe's structure. Moreover, the presence of dark energy complicates the puzzle even further. Believed to be responsible for the accelerated expansion of the universe, dark energy remains one of the most elusive and poorly understood aspects of modern cosmology. Its exact nature continues to baffle scientists, who now face the challenge of incorporating this enigmatic force into their models of the universe's evolution. In the quest to better understand the cosmic web and large-scale structures, researchers rely on sophisticated observational technologies and advanced computer simulations. These tools allow scientists to explore the universe's most fundamental mysteries, from the distribution of galaxies to the mysterious forces of dark matter and dark energy. But the questions remain: what is the exact role of dark energy in shaping the universe? What processes led to the formation of the cosmic web? And how did the universe transition from a uniform state after the Big Bang to the intricate web-like structure we see today? The answers to these questions lie in the ongoing work of cosmologists, whose discoveries continue to refine and reshape our understanding of the universe. The study of large-scale structures is a dynamic field, with models that evolve as new data is collected and new theories are tested. This constant adaptation fuels the excitement and wonder of discovery, as each new insight brings us closer to answering the profound questions that have intrigued humanity for centuries. In the context of the cosmic web, scientists have also been grappling with the transition from the universe's early homogeneous state to the complex and varied structure we observe today. After the Big Bang, the universe was a much more uniform place. Yet over billions of years, tiny density fluctuations began to grow, eventually leading to the formation of galaxies, galaxy clusters, and the vast voids between them. What triggered these fluctuations? How did the matter that once filled the universe become the intricate web we see today? These remain some of the most pressing questions in modern cosmology. Even as we uncover more details about the cosmic web and its formation, the full scope of its evolution remains elusive. While we know that dark matter plays a key role in shaping the universe's structure, the exact mechanisms behind its influence are still being explored. As researchers continue to delve into these cosmic mysteries, each discovery brings us one step closer to understanding the grand architecture of the universe and the forces that have shaped it. Thus, the study of large-scale cosmic structures, including quasars and the cosmic web, is not just about understanding the past, it is about predicting the future. By refining our cosmological models, we can better understand how the universe might evolve in the coming billions of years. This ongoing research not only helps us answer fundamental questions about the universe's origins, but also offers valuable insights into its future trajectory, deepening our connection to the cosmos and our place within it. The interactions between galaxies within the vast expanse of the cosmic web continue to present some of the most profound mysteries in modern astrophysics. These cosmic dances, which include galactic mergers and gravitational influences, reveal an intricate interplay that shapes the universe at the most fundamental level. As our technology advances, especially with the refinement of powerful telescopes and the increasing sophistication of computer simulations, scientists are hopeful that they will unlock the secrets of how the magnificent structures we observe today came to be. At the heart of these cosmic phenomena are galactic mergers. When two galaxies collide, they don't merely pass through each other. Instead, their gravitational interactions lead to remarkable transformations. These encounters are far from chaotic collisions in the traditional sense. They are orchestrated events that can trigger bursts of star formation. As dense clouds of gas within the merging galaxies collide and compress, the conditions become perfect for the rapid formation of new stars. This surge in star formation not only contributes to the overall mass of the resulting galaxy, but it also significantly enhances its brightness. Over the course of these mergers, galaxies undergo massive structural changes. What once might have been orderly spiral shapes could transform into chaotic elliptical forms, disrupting the galactic balance and giving rise to more complex dynamical properties. This disruption can also catalyze the growth of supermassive black holes at the centers of galaxies, further altering their evolution. Eventually, when two galaxies collide, their central black holes may merge as well, creating even more powerful black holes that can profoundly influence the surrounding galactic environment. These galactic mergers are not isolated events. Over the vast timeline of the universe, they contribute to the hierarchical model of galaxy formation. According to this model, smaller galaxies gradually merge to form larger ones, ultimately leading to the colossal structures that we observe in the universe today. Observations reveal that nearly every galaxy has undergone at least one significant merger throughout its history, with many having participated in multiple mergers over billions of years. Each merger doesn't just reshape the galaxies involved, it also contributes to the evolution of the large-scale structure of the entire cosmos. The aftermath of a galactic merger is equally fascinating. The remnants of such a cosmic event can result in a more stable galaxy, one that is more resistant to future interactions. However, even a stable galaxy can be prone to further mergers as galaxies continue to drift through space. These constant interactions fuel a dynamic cosmic environment, a cycle of creation and destruction that shapes the universe's future. In this ongoing process, each merger paves the way for the birth of new structures, ensuring the constant evolution of the cosmic landscape. While astronomers have made incredible strides in understanding dark matter, many aspects of its distribution and role on cosmic scales remain elusive. One of the greatest uncertainties concerns the organization of dark matter within the large structures of the universe, such as galaxy clusters and the intricate filaments that compose the cosmic web. Observations show that dark matter is not evenly spread throughout space. Instead, it tends to clump together under the influence of gravity, forming dense regions known as dark matter halos. This clumping behavior raises important questions about how these regions formed and evolved over time. Additionally, the nature of dark matter itself remains one of the universe's most profound mysteries. Leading theories suggest that dark matter is made up of particles that interact very weakly with ordinary matter, making it invisible and difficult to detect. However, despite decades of research, the exact particles responsible for dark matter remain unidentified, complicating our ability to accurately map its distribution in the cosmos. Current models of cosmic structure formation rely heavily on simulations based on assumptions about dark matter's properties. Yet these models continue to evolve as new data is gathered, refining our understanding of this elusive substance. As we continue to explore the universe, each new discovery brings us one step closer to unlocking the intricate mysteries of cosmic structure. The interactions between galaxies, the role of dark matter, and the complex dynamics of the cosmic web will continue to captivate scientists and stargazers alike, offering insights into the very fabric of the universe itself. The interaction between dark matter and the formation of galaxies presents a formidable challenge for researchers trying to understand the intricacies of the universe. Galaxies are believed to form within massive structures known as dark matter halos. Yet, the exact relationship between the properties of these halos and the observable characteristics of galaxies, such as their mass, size, and star formation rates, remains a complex and ongoing mystery. This lack of clarity raises fundamental questions about how closely dark matter is tied to the visible matter we can observe in galaxies. The investigation into these complexities continues to deepen our curiosity about the nature of both dark matter and the galaxies it helps to shape. Further complicating this puzzle is the large-scale structure of the universe, which is significantly influenced by dark matter. Its gravitational pull plays a crucial role in the cosmic scaffolding that governs the distribution of galaxies and other celestial objects. The quest to decipher the exact distribution of dark matter across vast cosmic scales is ongoing, as astronomers attempt to understand how it connects to various phenomena such as the cosmic microwave background radiation, an ancient relic from the early universe. As advancements in technology and observational techniques push the boundaries of what we can detect, scientists remain optimistic that we are on the verge of uncovering deeper, more profound insights into the elusive presence of dark matter and its role in the cosmos. In addition to dark matter's influence, another fascinating hypothetical concept captures the attention of scientists: cosmic strings. These are one-dimensional defects in the fabric of space-time, akin to cracks that form in a sidewalk after years of pressure. Predicted by certain physical theories, especially those concerning the universe's infancy, cosmic strings are believed to have emerged during the universe's rapid inflationary phase, right after the Big Bang. As the universe cooled, symmetry-breaking processes created these cosmic anomalies, much like how magnetic domains form when a magnet is subjected to external forces. The potential discovery of cosmic strings could revolutionize our understanding of the universe's structure. They are theorized to be incredibly dense and could produce intense gravitational fields strong enough to warp the surrounding space-time. This warping could in turn bend light and matter around them, leading to fascinating phenomena such as gravitational lensing. When light from distant objects passes near a cosmic string, it might be bent around the string, potentially resulting in multiple images of the same object, an effect scientists continue to study. While no direct evidence of cosmic strings has been found yet, the implications of their existence extend far beyond mere theoretical curiosities. If they do exist, their study could provide crucial insights into the unification of forces in physics, giving us glimpses into the conditions that prevailed shortly after the Big Bang. Understanding cosmic strings could also bridge the gap between general relativity, which describes the gravitational force at large scales, and quantum mechanics, which governs the interactions of subatomic particles. Thus, exploring cosmic strings is not merely an academic exercise. It may be the key to unlocking a deeper understanding of the fundamental forces that govern our universe. The search for cosmic strings is multifaceted, employing a variety of astrophysical techniques, including the analysis of cosmic microwave background radiation and gravitational wave detections. Researchers hope to discern whether these mysterious structures are real features of the universe or just theoretical constructs. The answer could significantly alter our comprehension of the cosmos, deepening our appreciation for its complex and interconnected architecture. Gravitational settling of matter plays a fundamental role in the intricate process of galaxy formation, a process that dates back to the very beginnings of the universe. Following the Big Bang, as the universe expanded, regions of space began to clump together under the influence of gravity. These clumps, composed of gas, dust, and dark matter, grew denser over time, leading to the formation of proto-galaxies, early structures that would eventually evolve into the galaxies we see today. This gravitational pull caused matter to settle and accumulate, creating the conditions needed for the birth of stars. As gas and dust consolidated within these dense regions, the conditions became favorable for nuclear fusion, the process that powers stars. The formation of stars not only marked the beginning of a new cosmic era, but also triggered a cascade of processes that would shape the evolution of galaxies. Newly formed stars released intense radiation and powerful stellar winds, both of which had a profound impact on their surroundings. These forces could drive away surrounding gas in some regions, while compressing it in others, fueling further star formation. This interplay of forces, the birth, death, and rebirth of stars, set in motion a dynamic cycle that continues to shape the galaxies. The gravitational settling of matter also influences the overall structure of galaxies. As stars form and burn through their nuclear fuel, they can end their lives in spectacular supernovae, scattering heavy elements back into space. This material often falls back into the galaxy, enriching the interstellar medium and contributing to the next generation of stars. This continuous cycle of stellar creation and destruction is driven by the gravitational forces acting on settled matter, and it has a direct impact on the overall morphology of galaxies. In this cosmic dance, dark matter plays an essential role. While ordinary matter, gas, dust, and stars, interacts with gravitational forces to form galaxies, dark matter provides the unseen scaffold that helps to hold galaxies together. The way matter settles within a galaxy is influenced by the presence of dark matter, which adds an extra layer of complexity to the process. As dark matter interacts with visible matter, it shapes the formation and structure of galaxies, influencing everything from their size to their star formation rates. The ongoing study of galaxy formation is a testament to the power of gravity and the mysterious presence of dark matter, which together govern the evolution of the cosmos. By unraveling the mechanisms behind gravitational settling and the role of dark matter, scientists hope to gain a deeper understanding of how galaxies form, evolve, and interact. In the end, this research may unlock the secrets of not just galaxies, but the very fabric of the universe itself. Spirals, ellipticals, and irregular galaxies, each category distinct in shape, structure, and behavior, owe their unique features to the intricate interplay of matter and gravity. This cosmic dance, sculpted over eons, tells the story of how the universe itself has evolved, offering profound insights into the nature of both our existence and the universe's broader history. Understanding how galaxies form and evolve under the ever-present force of gravity unveils crucial clues about the universe's fate, its expansion, and its possible end. At the heart of these cosmic phenomena lies a fundamental question: what role does the density of the universe play in shaping its future? The density of matter, or the amount of material packed into space, directly influences the gravitational forces that govern cosmic expansion. To grasp this relationship is to unlock the secrets of the universe's ultimate destiny. Essentially, the density of the universe dictates how it will evolve. Will it continue expanding forever? Will its expansion slow down? Or will it collapse in on itself in a dramatic, final act of cosmic implosion? Astronomers have identified three primary scenarios based on the universe's density relative to a critical threshold, a value that divides all possibilities. If the universe's density is higher than this critical value, it's considered closed. In a closed universe, gravity will gradually slow down the expansion, eventually halting it altogether, then reversing it. This process could lead to a big crunch, where all matter contracts and galaxies collide, coalescing into a singular, infinitely dense point. The end of everything, as it were, a dramatic collapse where all stars, planets, and galaxies are destroyed and reabsorbed back into an infinitely hot and dense singularity. However, if the universe's density is lower than this critical value, it is described as open. In this scenario, the universe would continue to expand, but at an ever-decreasing rate. Expansion would never stop completely, but galaxies would grow increasingly isolated from one another as the universe stretches out over trillions of years. Eventually, stars would burn out, galaxies would drift away, and the universe would cool into a state of eternal, lifeless stillness, a fate known as the heat death. This scenario presents a cold and desolate vision of the far-off future, where energy is scattered so thinly that it becomes unable to sustain life or structure, and the cosmos becomes a barren, empty expanse. The third possibility, often regarded as the most balanced, is the flat universe. In this case, the universe's density exactly matches the critical value. In this scenario, the expansion of the universe slows over time, asymptotically approaching but never quite reaching a halt. The universe would continue expanding forever, but at a slower and slower pace. This delicate equilibrium could, theoretically, keep the universe in a stable state for an indefinite period, though it would still be expanding just at an increasingly minimal rate. This scenario has gained significant support from current observations, particularly when considering the influence of dark energy, a mysterious force that is accelerating the expansion of the universe, counteracting the pull of gravity and pushing galaxies further apart. The precise role of dark energy in shaping the universe's future is still uncertain, but it adds an additional layer of complexity to the cosmic puzzle. At the same time, the universe's evolving structure is not limited to large-scale cosmic events. On a smaller scale, globular clusters, dense groups of stars orbiting the outer regions of galaxies, play a vital role in understanding the universe's history. These clusters, often packed with hundreds of thousands or even millions of stars, are some of the oldest and most mysterious structures we can observe. They are relics from the universe's early years, with some estimated to be nearly 12 billion years old. Their formation, however, remains an enigma. Scientists speculate that these clusters may have formed from the merging of smaller star groups or from the remnants of primordial gas clouds that existed in the universe's infancy. But the exact processes that led to their creation are still up for debate. One of the most fascinating characteristics of globular clusters is their stellar populations. Unlike the relatively uniform stellar makeup of younger star clusters, globular clusters often contain multiple populations of stars, groups of stars with different ages, chemical compositions, and physical properties. This diversity within a single cluster challenges our understanding of stellar evolution and raises intriguing questions. How did the first generation of stars within a cluster pave the way for later generations to form? Could these multiple populations be the result of complex processes such as gas mixing or the reuse of material in star formation? The mysteries surrounding globular clusters extend beyond their formation. Their fate, as they age, is equally perplexing. Despite their impressive longevity, globular clusters are not invincible. Over time, various forces, including tidal interactions with the host galaxy and gravitational encounters with other star clusters, can slowly strip a globular cluster of its stars or cause it to disintegrate altogether. Yet, some globular clusters persist, surviving far longer than others. What makes some clusters more resilient than others? What intrinsic characteristics allow certain clusters to withstand these cosmic challenges and persist for billions of years? These questions remain central to ongoing research, as astronomers seek to understand the forces that govern the longevity of these ancient stellar formations. Ultimately, both the fate of the universe and the longevity of globular clusters are tied to one overarching theme: gravity. This invisible force, which shapes the large-scale structures of the cosmos and governs the lives of stars, clusters, and galaxies, is a central player in the unfolding drama of the universe's evolution. Whether the universe continues to expand, collapses in a fiery crunch, or fades into cold emptiness, the influence of gravity will shape its destiny. Similarly, as globular clusters continue to orbit the outskirts of galaxies, they serve as living fossils of a past era, offering us valuable insights into the early days of the universe. Through the study of these cosmic entities, we deepen our understanding of the forces that have shaped and will continue to shape our ever-evolving cosmos. In addition to their captivating beauty, globular clusters have long been a source of scientific intrigue, particularly with the discovery of black holes hiding within them. Observations have led scientists to believe that intermediate-mass black holes could be lurking at the centers of some of these dense spherical groupings of stars. These black holes, with masses greater than stellar mass black holes but smaller than supermassive ones, might have formed through the merger of smaller black holes or from the collapse of exceptionally massive stars. The influence of these enigmatic objects on the dynamics of globular clusters presents an exciting area of research, offering potential insights into both stellar evolution and the fundamental nature of black holes themselves. By investigating how these black holes interact with the stars and gas surrounding them, astronomers gain a deeper understanding not just of individual stellar populations, but also of broader cosmic phenomena. This research extends far beyond globular clusters, tying in with the study of the larger-scale structure of the universe. In particular, the exploration of galaxy clusters provides another fascinating dimension of this cosmic investigation. Galaxy clusters are among the most massive and complex structures in the universe, consisting of dozens to thousands of galaxies bound together by the force of gravity. These clusters, some of the largest known gravitationally bound systems in the cosmos, offer a wealth of information about the universe's fundamental workings. To study them, researchers employ a combination of observational techniques and sophisticated theoretical models. Powerful ground-based and space-based telescopes, for instance, capture light across various wavelengths: optical, infrared, and X-rays. This multi-wavelength approach allows scientists to observe different components within the clusters: the galaxies themselves, the hot gas that fills the space between them, and even the invisible presence of dark matter. X-ray emissions are particularly invaluable for understanding the complex environment of galaxy clusters. The hot gas that pervades these clusters can reach temperatures of millions of degrees, causing it to glow brightly in the X-ray spectrum. By analyzing the intensity and distribution of these emissions, scientists can assess the thermal dynamics of the gas and estimate the mass of the entire cluster. This, in turn, provides critical insights into the gravitational interactions occurring between galaxies and helps scientists map out the mass distribution across the cluster. Notably, this includes dark matter, which is invisible to traditional telescopes, but has a profound influence on the structure of the universe. In addition to observational data, simulations play a pivotal role in studying the dynamics of galaxy clusters. By creating computer models that simulate the gravitational interactions within these clusters, scientists can test and refine their understanding of how these immense structures form and evolve over time. Comparing these simulations with real-world data allows researchers to answer fundamental questions about the nature of matter in extreme gravitational environments, the role of dark energy, and the ultimate fate of the universe. Galaxy clusters, in essence, serve as cosmic laboratories that provide critical insights into the grand-scale structure of the universe. The study of these clusters helps to unlock some of the most profound mysteries of the cosmos. It sheds light on the processes that govern galaxy formation and evolution, the influence of dark matter in shaping visible structures, and the overall dynamics of large-scale cosmic systems. Each galaxy cluster carries within it the fingerprints of the universe's history, offering clues about the past and, potentially, hints about its future. As such, these clusters act as time capsules, preserving the chaotic and turbulent moments of cosmic evolution and providing a glimpse into the universe's expanding future. Equally important in our understanding of the cosmos is the cosmic microwave background, CMB, a faint but profound radiation that permeates all of space. This relic from the early universe, known as the afterglow of the Big Bang, dates back to around 380,000 years after the event, when the universe had cooled enough for protons and electrons to combine into neutral hydrogen atoms. This shift in matter allowed light to travel freely, creating the CMB that we detect today. The CMB holds crucial clues about the state of the universe during its infancy. One of the most compelling features of the CMB is the tiny fluctuations in temperature that can be detected across the sky. Although these variations are minuscule, they carry vital information about the density, composition, and evolution of the universe. By meticulously mapping these fluctuations, scientists can trace the origins of the galaxies and large-scale structures that began to form in the early universe. This analysis offers a deeper understanding of how the cosmos grew from a hot, dense state to the vast, intricate structure we observe today. Moreover, the CMB provides valuable insights into key cosmological parameters. For instance, by studying the CMB's characteristics, physicists have been able to refine their models of cosmic evolution and make predictions about the universe's fate. Notably, data gathered from the CMB has revealed that the universe is composed of roughly 70% dark energy, 25% dark matter, and only about 5% ordinary matter. These revelations have reshaped our understanding of the cosmos, highlighting the immense role of dark energy and dark matter in shaping the universe's structure and future. In essence, the study of galaxy clusters and the cosmic microwave background not only unveils the intricate processes that govern cosmic structures, but also provides fundamental insights into the origins, composition, and ultimate fate of the universe. Both offer a window into the universe's vast history and a glimpse into the ongoing evolution of the cosmos, revealing the forces that will shape the universe for eons to come. The cosmic microwave background, CMB, serves as a celestial laboratory, offering profound insights into the earliest stages of the universe. This faint glow, left over from the Big Bang, is not only a relic of cosmic history, but also an invaluable tool for testing theories that challenge the boundaries of current physics. Any anomalies observed in the CMB data can potentially point to new physics beyond what is currently understood, inviting fresh hypotheses about the fundamental forces and particles that govern the cosmos. This exploration is more than a mere pursuit of knowledge. It is a step toward uncovering a unified theory capable of explaining the behavior of all forces in nature. The discoveries made through the study of the CMB contribute to our ongoing quest to understand the very fabric of the universe, laying the foundation for future breakthroughs that could forever alter our perception of reality. As we continue to probe the mysteries of space, several innovative technologies are emerging as frontrunners for future space exploration. One of the most exciting advancements is the development of advanced propulsion systems, particularly those utilizing ion propulsion. This cutting-edge technology works by harnessing electric fields to accelerate ions, enabling spacecraft to achieve significantly higher speeds and travel vast distances without the need to carry large amounts of fuel. The implications of this are immense, as ion propulsion systems could enable missions to distant planets and even pave the way for interstellar travel, opening up entirely new frontiers for human exploration. In addition to propulsion advancements, robotics and artificial intelligence, AI, are playing an increasingly vital role in space exploration. These technologies are becoming essential for both autonomous and semi-autonomous spacecraft, which rely on advanced AI to perform a wide array of tasks. Robots equipped with state-of-the-art sensors can conduct scientific experiments on distant moons and planets, gather data, and perform repairs, all without putting human lives at risk. These autonomous systems enhance our ability to explore the most extreme and remote environments within our solar system, providing critical insights into regions that might one day become targets for human missions. The role of robotics in space exploration is rapidly expanding, offering new possibilities for scientific discovery and technological advancement. Moreover, breakthroughs in material science are playing a pivotal role in revolutionizing spacecraft design. The development of lightweight, durable materials capable of withstanding the harsh conditions of space travel is essential for the safety and longevity of missions. For example, advanced thermal protection systems constructed from high-performance composites and heat-resistant ceramics are designed to protect spacecraft during intense heat events, such as re-entry into Earth's atmosphere. These resilient materials not only ensure the safety of astronauts and equipment, but also extend the operational lifespan of spacecraft, making long-duration missions more feasible and efficient. Life support technologies are also undergoing significant advancements, critical for enabling human missions to distant planets such as Mars. Innovations in recycling air and water, growing food in space, and managing waste are essential components of ensuring astronauts can survive and thrive on other planets for extended periods. These technologies have the potential to fundamentally transform space exploration, allowing humans to establish a sustainable presence beyond Earth. As we push the boundaries of what is possible in space exploration, Each leap forward in these fields brings us closer to realizing a future where humanity becomes a multiplanetary species. One of the most profound and transformative endeavors in space exploration is the search for extraterrestrial life. The discovery of even the simplest forms of life beyond Earth would dramatically reshape our understanding of life itself. It would challenge the assumption that life is a unique phenomenon, suggesting that the ingredients necessary for life might be more universal than previously thought. This realization could fundamentally alter our understanding of biology, evolution, and the potential for life to exist elsewhere in the cosmos. The possibility that life might exist on other planets would inspire a re-evaluation of what constitutes life, encouraging researchers to expand the definition to include forms of biology that could thrive in conditions vastly different from those found on Earth. Furthermore, the search for extraterrestrial intelligence raises profound philosophical and existential questions. What would it mean for humanity to discover intelligent life beyond our planet? How would such a discovery impact our culture, technology, and even our political systems? These questions are not purely speculative. They offer a glimpse into the potential future of human civilization. The revelation that we are not alone in the universe could unite humanity, shifting our focus away from terrestrial concerns and toward a broader, more cosmic perspective. In the pursuit of extraterrestrial life, the tools and technologies we develop are pushing the limits of human capability. Robotic spacecraft, advanced space telescopes, and interstellar survey techniques are enabling us to gather more data about the universe than ever before. These advancements not only deepen our understanding of the cosmos, but also drive forward innovation in science and engineering. Every new discovery, whether it is a signal from an alien civilization or evidence of microbial life on an exoplanet, generates new questions, sparking a continuous cycle of inquiry that propels humanity ever closer to unraveling the mysteries of the universe. Among the most intriguing and unexplored territories in our solar system are the icy moons of Jupiter and Saturn. These moons are considered some of the most promising sources of discovery, particularly when it comes to the search for life beyond Earth. Europa, one of Jupiter's moons, captivates scientists with its subsurface ocean concealed beneath a thick layer of ice. This hidden ocean may hold the key to understanding the potential for life on distant worlds. In addition to the possibility of harboring life, Europa's unique geological features, such as ice plumes that periodically shoot into space, may offer clues to chemical processes occurring beneath the surface, similar to those on Earth. Researchers believe that the ocean may be in contact with Europa's rocky mantle, potentially creating the conditions necessary for life as we know it. Enceladus, a small moon of Saturn, offers a similar allure. It has been observed ejecting geysers of water vapor and ice particles from its south pole, suggesting the presence of a subsurface ocean. In 2005, the Cassini spacecraft detected organic molecules in these plumes, further heightening interest in this icy world. The interaction between heat generated by tidal forces and the potential for hydrothermal vents on the ocean floor raises the tantalizing possibility that life might exist in these remote, frozen worlds. Enceladus, like Europa, represents a unique opportunity to explore a potentially habitable environment far beyond the familiar conditions of Earth. Beyond the icy moons, the dwarf planet Pluto, with its heart-shaped glacier known as Sputnik Planitia, remains one of the least explored worlds in our solar system. The New Horizons mission, which passed by Pluto in 2015, revealed a complex landscape featuring icy mountains and signs of possible geological activity. Scientists are eager to further investigate Pluto's geology and atmosphere, as understanding these features could shed light on the formation and evolution of similar bodies within the Kuiper Belt. Pluto remains an enigmatic world, and ongoing research into its composition and history could unlock secrets about the outer reaches of our solar system and the forces that shaped its distant planets and moons. Each of these frontiers, whether it's the study of the CMB, the search for extraterrestrial life, or the exploration of distant moons and planets, represents a critical step forward in our journey of cosmic discovery. The tools we develop, the questions we ask, and the boundaries we push all serve as a testament to humanity's insatiable curiosity and drive to understand the universe and our place within it. The mysteries of the cosmos are vast, but with each advancement, we are one step closer to unraveling them. The study of comets opens up yet another exciting frontier for discovery in the cosmos. These ancient celestial wanderers, believed to be remnants of the early solar system, contain primordial materials that date back to its formation. By analyzing the composition of these icy bodies, scientists hope to unlock secrets about the early conditions in the solar system, knowledge that could shed light on the origins of organic molecules essential for the development of life on Earth. As we continue to study these frozen relics, there is the potential for groundbreaking revelations that may reshape our understanding of life's origins, the history of our solar system, and the broader universe. The exploration of comets is a crucial piece in the puzzle of cosmic history, holding keys to untold mysteries. Advancements in artificial intelligence, AI, are poised to radically transform space exploration. One of the most significant contributions of AI to this field lies in its unparalleled ability to process vast amounts of data at incredible speeds. Space missions, whether they involve telescopes peering into the far reaches of the galaxy or rovers exploring the barren surfaces of distant planets, generate enormous volumes of information. AI is capable of analyzing this data, identifying intricate patterns, and making predictions, tasks that would be nearly impossible for human scientists to perform unaided. Through these capabilities, AI can assist in extracting valuable insights from complex data sets, allowing humanity to uncover secrets hidden in the depths of space. AI also enhances the autonomy of spacecraft and rovers. As missions venture farther from Earth, the vast distances involved make real-time communication increasingly difficult. Autonomous systems powered by AI can make decisions independently based on local conditions, without the need for immediate input from Earth. For instance, if a rover on Mars encounters an unexpected obstacle, AI systems can analyze the situation in real time, weigh the possible solutions, and determine the best course of action, all while sending data back to Earth for further analysis. This level of autonomy is critical for the success of long-duration missions, especially as space exploration pushes further into the unknown. Moreover, AI plays a pivotal role in spacecraft design and simulation. By leveraging machine learning algorithms, researchers can optimize spacecraft components to enhance their performance, efficiency, and durability. This has the potential to reduce both the cost and time associated with mission planning and manufacturing. AI can simulate different scenarios, helping scientists predict how spacecraft will respond in the harsh conditions of space, from extreme temperatures to intense radiation exposure. This advanced predictive power not only streamlines the design process, but also ensures that spacecraft are better equipped to handle the rigors of deep space exploration. AI is also revolutionizing the search for extraterrestrial life. Through its ability to process complex signals from space and analyze data from planetary atmospheres, AI can assist in identifying potential biosignatures, chemical indicators that may suggest the presence of life. The implications of this development are profound. It brings us one step closer to answering one of humanity's most pressing questions. Are we alone in the universe? As AI continues to evolve, its applications in space exploration will expand, opening up new frontiers in our understanding of life beyond Earth and the cosmos itself. Several groundbreaking projects on the horizon promise to drastically alter our understanding of the universe. The James Webb Space Telescope, launched at the end of 2021, is one such project. With its advanced infrared capabilities, it is designed to peer into the distant past, observing light emitted by celestial objects billions of years ago. By studying the formation of stars and galaxies in the early universe, the James Webb Telescope promises to provide insights into cosmic evolution that were previously beyond our reach. Another monumental project is the Extremely Large Telescope ELT, currently under construction in Chile. With a mirror measuring over 39 meters in diameter, it will become one of the largest optical telescopes ever built. This massive facility will allow astronomers to study the atmospheres of exoplanets, investigate the mysteries of dark matter, and explore the intricate processes behind galaxy formation. Its high-resolution observations will provide an unprecedented view of the universe, unveiling details that were once thought impossible to observe. The Square Kilometre Array, SKA, a groundbreaking radio telescope project spanning Australia and South Africa, is set to revolutionize our understanding of the cosmos. By linking thousands of individual antennas, the SKA will function as one massive radio dish, enabling scientists to probe the origins of cosmic magnetism, study the formation of the first stars, and examine the distribution of dark energy. The insights gained from this massive project could dramatically alter our understanding of the universe's structure and its ongoing evolution. Additionally, the European Space Agency's Ariel mission, set to launch in the coming years, will focus on studying the atmospheres of exoplanets through spectroscopy. By analyzing the chemical composition and weather patterns of these distant worlds, Ariel aims to provide crucial information about how planetary systems form and evolve. These telescopes and missions represent the cutting edge of cosmic exploration, offering the promise of uncovering profound secrets about the universe's hidden depths. As humanity looks to the future, the exploration of Mars stands as one of the most tantalizing prospects in planetary science. Mars offers a unique opportunity to study a planet that once harbored conditions strikingly similar to those of early Earth. By sending astronauts to Mars, scientists hope to gather direct evidence of its geological history and climatic changes over billions of years. Through detailed analysis of Martian rocks and soil, researchers can uncover insights into the planet's volcanic activity and water history, critical factors that have shaped its evolution. Studying how Mars transitioned from a warmer, wetter environment to its present cold, arid state could reveal valuable lessons about the conditions required for life to thrive. By comparing the evolutionary paths of Mars and Earth, we gain a deeper understanding of how planetary processes influence habitability. Mars provides a mirror through which we can better comprehend our own planet's past and future, and perhaps even identify what might have prevented life from flourishing there. In exploring Mars, we are not just examining a neighboring planet. We are expanding our knowledge of planetary evolution, habitability, and the complex dynamics that shape celestial bodies. With every mission, experiment, and discovery, humanity moves closer to answering fundamental questions about life and the forces that govern the universe. Through artificial intelligence, advanced telescopes, and human exploration, the mysteries of the cosmos are slowly unfolding, revealing a universe far richer and more complex than we ever imagined. Human exploration of space offers invaluable opportunities to investigate distant worlds in ways that robotic missions simply cannot match. Astronauts, equipped with cutting-edge scientific tools and instruments, are able to conduct real-time observations and experiments, providing insights that are both immediate and precise. Unlike robotic probes, humans can engage in the nuanced investigation of specific sites using their adaptability to assess conditions with unmatched accuracy. For example, astronauts on Mars could directly analyze the effects of solar radiation on Martian regolith or search for signs of past microbial life in ancient lake beds, tasks that would remain beyond the reach of unmanned missions. These first-hand encounters with alien environments could answer questions that would otherwise remain mysteries, even with the best remote data available. By comparing the geological and atmospheric data gathered from Mars to Earth's own, scientists can test and refine theories about the formation and evolution of planetary bodies. This comparative approach not only deepens our understanding of Mars, but also sheds light on the processes that shape all rocky planets, including Earth. Understanding these processes could have profound implications for our knowledge of climate dynamics, geological activity, and the very potential for life elsewhere in our solar system and beyond. The exploration of Mars and the discoveries that could emerge from it would therefore be a crucial piece of the larger puzzle. It would enhance our understanding not only of Mars itself, but also of the fundamental processes that govern the development of planetary systems. Past space missions have already significantly shaped our perception of the universe, with iconic endeavors like Voyager and Hubble revealing vast cosmic phenomena. These discoveries have forced scientists to rethink everything from the origins of our solar system to the possibility of life existing beyond Earth. For instance, findings related to the atmospheres of exoplanets or the geological features of Mars are not just isolated observations. They serve as foundational data that continue to inform future exploration and hypothesis building. As we look to the future, these monumental missions have laid the groundwork for new explorations. The detection of water on Mars, for instance, has sparked renewed interest in the possibility of microbial life lurking beneath its surface, prompting future missions that not only aim to observe, but to collect samples, paving the way for human exploration. Each new mission builds upon the knowledge of its predecessors, allowing space agencies to make more informed strategic decisions about where to allocate resources for maximum impact. Technological evolution plays a pivotal role in this progression. Innovations that arose from earlier space exploration have resulted in significant improvements in spacecraft design, imaging technologies, and data analysis methods. The lessons learned from past missions are used to refine our approach to new challenges, developing more advanced instruments for studying distant worlds. This ongoing cycle of learning and refinement ensures that we continue to push the boundaries of what's possible in space exploration. Moreover, the collaborative spirit that has emerged in space exploration cannot be overlooked. As nations and organizations around the globe recognize the mutual benefits of pooling resources and expertise, the future of space exploration looks increasingly interconnected. Together, we share the knowledge, technology, and vision that will guide humanity into the unknown. The cumulative insights gained from past and ongoing missions not only chart the course for scientific inquiry, but also ignite the imaginations of future explorers eager to unlock the mysteries of the universe. One area of exploration that is gaining unprecedented attention is astrobiology, the study of life in the universe. This interdisciplinary field draws on biology, chemistry, geology, and astronomy to understand the origins, evolution, distribution, and future of life beyond Earth. Recent advances in astrobiology have been fueled by the study of extremophiles, organisms that thrive in Earth's most hostile environments. These remarkable creatures have been found to endure extreme heat, acidity, and radiation, challenging our previous assumptions about where life can exist. Their resilience suggests that life might be able to survive in similarly harsh conditions elsewhere in the universe. Astrobiology has also been propelled forward by the exploration of other worlds within our solar system. Mars, for example, has revealed ancient riverbeds and mineral deposits that imply the presence of liquid water in its distant past. Recent discoveries of organic compounds in Martian soil further fuel the hypothesis that life might have once existed there. In addition to Mars, icy moons such as Europa and Enceladus orbiting Jupiter and Saturn have garnered significant interest due to the discovery of subsurface oceans and the presence of essential chemical ingredients for life. These findings are shaping the next generation of astrobiological research, allowing scientists to refine their understanding of what conditions are necessary for life to emerge and survive. The development of powerful telescopes, like the James Webb Space Telescope, has revolutionized our approach to searching for life beyond our solar system. By examining the atmospheres of exoplanets, planets orbiting stars outside our solar system, astronomers can identify telltale signs of life, such as oxygen or methane. The detection of such biosignatures provides crucial clues about the habitability of distant worlds, expanding our understanding of where life might exist and how it might manifest. As scientists continue to refine their methods for detecting biosignatures, the implications for astrobiology are profound. Each new discovery, whether it supports or challenges our notions about life beyond Earth, brings us one step closer to answering one of humanity's oldest questions. Are we alone in the universe? The pursuit of these answers not only enriches our understanding of life on Earth, but also expands our perspective on the diversity and possibilities of life in the cosmos. Astrobiology, then, is more than just a scientific endeavor. It is a philosophical exploration that challenges our assumptions about life's uniqueness and its potential for variety across the universe. It encourages us to consider what it means to be human and what our place might be in the vast, interconnected cosmos. Whether or not we find definitive evidence of extraterrestrial life, the quest itself has already broadened our view of the universe and deepened our connection to it. In the coming years, a number of promising missions are set to further our understanding of the outer solar system. These missions will continue to build upon the knowledge gathered from previous explorations, adding new dimensions to our understanding of planetary bodies, their potential for life, and the conditions required for such life to exist. As we venture further into the unknown, we are reminded that each discovery, no matter how small, brings us closer to answering one of the most profound questions humanity has ever asked. Is there life beyond Earth? And if so, what does it mean for us? In the early years of the next decade, one of the most exciting endeavors in space exploration will take flight: NASA's Europa Clipper mission. This ambitious spacecraft is set to embark on a groundbreaking journey to Jupiter's icy moon, Europa, a celestial body that has long captivated the imagination of scientists. What makes Europa so intriguing is its subsurface ocean, a vast body of water hidden beneath miles of ice. This ocean is believed to harbor the necessary conditions that could support life. The Europa Clipper mission aims to conduct detailed reconnaissance, probing the moon's thick, icy shell, surveying its surface chemistry, and ultimately exploring its potential habitability. In doing so, the mission could unlock answers to one of humanity's most profound questions: are we alone in the universe? But Europa is not the only moon drawing attention. Another ambitious project that is capturing the imagination of scientists around the world is NASA's Dragonfly mission. Slated for launch in the mid-2020s, Dragonfly will venture to Titan, Saturn's largest moon, where the possibility of discovering prebiotic chemistry or even life exists. What sets Dragonfly apart is its innovative design as a rotorcraft, essentially a flying drone, that will allow it to explore Titan in ways never before possible. Unlike conventional landers, Dragonfly will have the mobility to examine diverse sites across the moon's surface. Titan's mysterious liquid hydrocarbon lakes and its thick, nitrogen-rich atmosphere will be among the key areas of exploration. By studying the moon's atmospheric and geological features, Dragonfly will help us understand the unique chemistry at play on Titan, potentially revealing the building blocks of life beyond Earth. Meanwhile, across the Atlantic, the European Space Agency is contributing its own efforts to unravel the mysteries of the outer solar system. The Jupiter Icy Moons Explorer, JICE, mission is set to launch around the same time as Europa Clipper and will focus on Jupiter and its three largest icy moons, Ganymede, Callisto, and Europa. JICE's goal is to investigate the icy shells of these moons, seeking signs of the oceans that lie beneath. This mission will also aim to explore the potential for life in these distant water worlds, while deepening our understanding of the processes that have shaped their evolution. Together with Europa Clipper and Dragonfly, JICE represents a monumental leap in our exploration of the outer solar system. These missions are not only poised to deepen our knowledge of distant worlds, but they may also reveal crucial insights into the conditions required for life to exist elsewhere in the cosmos. As these spacecraft venture farther from Earth, they will also bring us closer to understanding cosmic radiation, a force that plays a significant role in the future of space travel. Cosmic radiation consists of high-energy particles that originate from various astronomical sources, including supernovae and black holes. These particles are dangerous for astronauts as they pose serious health risks, such as increased cancer rates and other long-term ailments, due to their ability to penetrate through matter. By studying cosmic radiation in depth, scientists aim to develop better shielding techniques for spacecraft, ensuring that future crews are protected during long-duration missions, especially as we set our sights on destinations beyond our solar system. An informed approach to cosmic radiation could dramatically enhance mission planning. Understanding radiation patterns and how they vary in different regions of space would allow researchers to identify safer travel paths for spacecraft, optimizing their routes to minimize exposure. Some parts of space are known to have higher radiation levels due to galactic phenomena, while others might offer more shielding. By charting a careful course through these zones, space agencies can improve astronaut safety and increase the chances of mission success. Beyond merely protecting astronauts, cosmic radiation could potentially be harnessed as a source of energy. Advanced technology may one day allow spacecraft to convert cosmic radiation into usable energy, providing an alternative to traditional fuel sources. This breakthrough could make long-duration missions, especially those venturing deep into the cosmos, more sustainable and feasible. As humanity looks toward the stars, mitigating the harmful effects of cosmic radiation and finding ways to use it to our advantage could open entirely new frontiers in space exploration. Each new discovery in this field pushes the boundaries of our understanding, not only about the universe, but also about our place within it. The spirit of exploration and innovation is what drives humanity to expand its reach, to challenge the limits of what we know, and to look toward a future where the vastness of space is no longer a mystery, but a realm waiting to be explored. As we delve into the origins of the universe, several theories attempt to explain how it all began. The most widely accepted of these is the Big Bang theory. This theory posits that the universe originated from an infinitely small, dense point approximately 13.8 billion years ago. This point rapidly expanded, leading to the formation of matter, energy, galaxies, and all the cosmic structures we observe today. Critical evidence, such as the cosmic microwave background radiation and the observable redshift of distant galaxies, strongly supports this theory. However, there are alternative ideas that have also shaped our understanding of the universe's origins. One such concept is the steady-state theory, which was popular in the mid-20th century. This theory proposed that the universe is eternal and unchanging on a large scale, asserting that as it expands, new matter is continuously created to fill the gaps. While it offered a counterpoint to the Big Bang, the steady-state model has largely fallen out of favor, as observations suggest that the universe is dynamic and constantly evolving. Another alternative is the cyclic model, which presents a fascinating idea that the universe undergoes infinite cycles of expansion and contraction. According to this theory, after each Big Bang, the universe expands, only to eventually collapse back into a singularity, leading to a new Big Bang. This cyclical process might offer profound insights into the nature of time and the forces that govern the cosmos. As we continue to explore these various theories, new data may provide clarity, offering us a deeper understanding of the universe's grand narrative. The exploration of our universe, from the icy moons of Jupiter to the mysteries of cosmic radiation, is only just beginning. Each mission, each discovery, brings us closer to understanding the cosmos and our place within it, driving the human spirit of inquiry and pushing the boundaries of what is possible in the quest for knowledge. Quantum theories and multiverse hypotheses introduce even greater complexity to our understanding of the cosmos, pushing the boundaries of what we perceive as reality. These ideas suggest that the universe we inhabit is just one of an infinite number of universes, each with its own unique set of physical laws and constants. In such a multiverse, quantum fluctuations, minute, random shifts in energy, could spark the creation of entirely new universes, expanding the scope of existence beyond our imagination. Each of these theories offers a distinct lens through which we can examine cosmic phenomena, each highlighting different aspects of the universe's formation and evolution. They collectively invite ongoing exploration and debate, urging scientists to dig deeper into the mysteries surrounding the origins of everything we know. To navigate this complex terrain, researchers rely heavily on advanced computer simulations, which serve as essential tools for building intricate models of the universe's evolution. These models allow scientists to explore processes that are otherwise impossible to observe directly, offering insights into the behavior of cosmic structures across vast stretches of time. Through these simulations, researchers can replicate the evolution of the universe from the earliest moments, such as the formation of the first stars, all the way to the clustering of galaxies. By inputting known physical laws and specific initial conditions, they are able to recreate various scenarios that show how the universe would evolve under different influences. A critical feature of these simulations is their ability to account for some of the universe's most enigmatic elements: gravity, dark matter, and dark energy. Gravity, the fundamental force that governs the attraction between masses, plays a pivotal role in shaping the universe. It helps matter coalesce into galaxies and galaxy clusters, influencing the very structure of the cosmos. Dark matter, while invisible, constitutes a significant portion of the universe's mass. Its presence affects the motion of visible matter, pulling galaxies and other structures together in ways that cannot be explained by gravity alone. Dark energy, on the other hand, is the mysterious force believed to be responsible for the accelerating expansion of the universe. By incorporating these three elements into simulations, scientists can track how the universe evolved from a hot, dense state to its current cold and largely empty expanse. The ability to run such simulations also allows scientists to test competing theories about the universe's formation and behavior. They can explore different models of cosmic inflation, the rapid expansion of the universe shortly after the Big Bang, or experiment with various theories about the nature of dark energy. By comparing the outputs of their simulations with real observational data, such as the cosmic maps generated by powerful telescopes, researchers can refine their models and improve their understanding of the universe's underlying structure. This iterative process not only helps address discrepancies in current theories, but also opens new avenues for scientific inquiry. As technology progresses, the fidelity and accuracy of these simulations continue to improve. Today, scientists are able to simulate billions of particles across millions of light years, capturing the complexity of reality in unprecedented detail. These advances are not just about understanding the universe's past, they are also about predicting its future. With the help of sophisticated simulations, we can gain insight into possible scenarios that may unfold billions of years from now, from the eventual fate of the cosmos to the long-term behavior of its most distant regions. However, one of the greatest challenges in modern physics remains the quest to unify general relativity and quantum mechanics, two foundational theories that describe different aspects of reality. General relativity explains gravity as the curvature of space-time caused by mass and energy, while quantum mechanics governs the behavior of particles on the smallest scales. The disparity between these two theories becomes particularly problematic in extreme conditions, such as the dense, hot environments found in black holes or in the moments immediately after the Big Bang. These conditions call for a new framework that can reconcile both the smooth, continuous nature of space-time described by general relativity and the probabilistic, discrete nature of the quantum world. One of the most prominent approaches to solving this problem is string theory, which suggests that the fundamental building blocks of the universe are not point particles, as traditionally thought, but rather tiny, vibrating strings. These strings, which exist in multiple dimensions, give rise to various particles through their different vibrational modes. String theory offers a promising framework that naturally incorporates gravity while also aligning with the principles of quantum mechanics. However, its full implications remain a subject of intense study and debate. Another approach gaining traction is loop quantum gravity, which proposes a radical rethinking of space-time itself. Instead of treating space-time as a smooth continuum, this theory envisions it as a network of interconnected loops, suggesting that at the smallest scales, space is not continuous, but granular. Loop quantum gravity preserves the predictions of general relativity at larger scales while directly incorporating quantum mechanics into the fabric of spacetime. This perspective allows for the possibility of a finite, discrete universe, addressing some of the most significant challenges in our understanding, such as the singularities found at the centers of black holes. The journey toward a comprehensive theory of quantum gravity is far from over, but the progress made so far has inspired a new generation of physicists. As research advances, the hope is that a unified theory will not only resolve fundamental conflicts, but also open new windows into the mysteries of the universe, potentially revealing phenomena beyond our current comprehension. The pursuit of this elusive theory continues to drive the frontiers of science, with each discovery offering a piece of the cosmic puzzle that has intrigued humanity for centuries. The implications of recent discoveries in theoretical physics have the potential to fundamentally alter our understanding of reality and our place in the vast expanse of the cosmos. One of the most revolutionary concepts that has reshaped our perception is string theory, which challenges the traditional framework of fundamental physics. Instead of viewing the basic building blocks of the universe as point-like particles, string theory posits that they are, in fact, tiny vibrating strings. These strings, though incredibly small, on the scale of the Planck length, which is far beyond the resolution of our current experimental techniques, are the foundation for everything that exists in the universe. Each vibration mode of these strings corresponds to a different type of particle, including those responsible for the four fundamental forces that govern our world: gravity, electromagnetism, and the strong and weak nuclear forces. This introduces a profound idea: the possibility of unifying all the fundamental forces under one cohesive theoretical framework. In traditional physics, gravity and quantum mechanics have been treated as separate realms, leading to inconsistencies when attempting to explain phenomena that occur at the quantum level. For example, near black holes or during the early moments of the universe, these two frameworks fail to provide a complete explanation. String theory, however, offers a potential solution by showing how all forces might arise from different string vibrations, merging previously separate domains into a unified theory of everything. But that's not all. String theory also suggests that our universe contains more dimensions than the four we experience: 3 of space and 1 of time. While we perceive the world around us in these 4 dimensions, string theory proposes the existence of additional hidden dimensions, potentially 6 or 7 more, that are compactified or curled up in ways that are undetectable at the scales we are familiar with. These extra dimensions could have far-reaching implications, potentially explaining how forces interact and even accounting for the variations in particle mass and charge that we observe in nature. Such a revelation could reshape the very foundation of our reality, opening up new avenues of exploration in theoretical physics. At the heart of this pursuit lies an even more profound question: what is the true nature of reality itself? As researchers dive deeper into string theory and other advanced concepts, they are not only investigating the fundamental forces, but also challenging our understanding of space, time, and matter. String theory, with its unifying framework and hidden dimensions, continues to drive innovation in physics, inspiring new ideas, theories, and research. These explorations are pushing the boundaries of our comprehension, prompting us to rethink everything from the smallest subatomic particles to the structure of the cosmos itself. The very fabric of our universe may be far more intricate and complex than we ever imagined. Simultaneously, our understanding of cosmology, the study of the universe as a whole, is also undergoing a transformation. The Big Bang Theory, which has long been the cornerstone of our knowledge about the origins of the universe, suggests that everything we observe today originated from an incredibly hot and dense state roughly 13.8 billion years ago. This theory has provided valuable insights, but it is not without its challenges. Recent advances in technology, particularly the use of powerful telescopes, have allowed scientists to gather more data from the cosmic microwave background radiation, a faint glow left over from the Big Bang. This radiation holds essential information about the conditions of the early universe and provides strong support for many aspects of the Big Bang model. Yet, as we look deeper into the cosmos, we encounter phenomena that complicate our current theories. For example, the unexpected formation of galaxies earlier than anticipated has raised questions about the accuracy of our models of cosmic inflation, the rapid expansion of the universe immediately following the Big Bang. Discoveries like these may force scientists to reevaluate existing theories or even develop entirely new models of the universe's evolution. Furthermore, emerging ideas such as quantum gravity challenge the traditional interpretation of the Big Bang itself, suggesting that the universe may not have had a single beginning, but could instead be part of an ongoing cycle of expansion and contraction. These revolutionary ideas are reshaping the landscape of cosmology. They suggest that the universe's origins may not be as straightforward as we once believed. The interplay between established evidence and newly discovered anomalies is guiding us toward a more nuanced understanding of the cosmos. In fact, some cosmologists are beginning to explore alternative models of the universe, including cyclic universes. These models propose that the universe undergoes endless cycles of expansion and contraction, each cycle resetting the conditions of the universe. This challenges the traditional view of a singular beginning to the universe, and instead suggests that cosmic evolution is a never-ending process with no definitive starting or ending point. As these theories continue to evolve, we are left with more questions than answers, but also with a deeper appreciation for the mysteries of the universe. Each new discovery brings us closer to a more comprehensive picture of the cosmos, and with it, a deeper understanding of the forces that govern everything, from the smallest particles to the vast reaches of space. The quest for knowledge in astrophysics and cosmology is a continuous journey, and as we push the boundaries of our understanding, we are reminded that the universe is far more complex and extraordinary than we could have ever imagined. The story of the cosmos is still unfolding, and every breakthrough takes us one step closer to uncovering its secrets. Cyclic models of the universe, long considered speculative, have emerged as compelling alternatives in modern cosmology, offering intriguing explanations for cosmic phenomena that have long remained enigmatic. Among these phenomena are the uniformity of the cosmic microwave background radiation and the large-scale distribution of galaxies, both of which have puzzled scientists for decades. These alternative models, which suggest the universe undergoes an endless series of cycles, each beginning with a Big Bang and ending in a Big Crunch, provide a fresh perspective on fundamental questions about the origin, structure, and ultimate fate of our cosmos. If the universe is indeed cyclical, it opens up new avenues for discussion, particularly regarding the concept of entropy, which is governed by the second law of thermodynamics. In the context of a cyclical universe, questions arise about how the total entropy might behave across multiple cycles. Does it reset with each Big Bang, or does it accumulate with every cycle, gradually affecting the universe's properties? Additionally, the cyclical model challenges our very understanding of time. Could time itself have a beginning and end only to start anew in an endless loop, or does time behave in ways far more complex than current models suggest? As cosmologists probe these theories, they aim to weave together diverse threads of knowledge, attempting to create a more unified theory that can explain everything from the subatomic intricacies of quantum mechanics to the grand cosmic structures like galaxies, superclusters, and voids. The vast diversity of thought surrounding cosmological models reflects the scientific community's tireless pursuit to push the boundaries of human understanding. By rigorously exploring these alternative theories, scientists don't just challenge established paradigms. They enrich the very discourse that drives the progression of knowledge, potentially opening the doors to groundbreaking discoveries that could redefine our perception of the universe and our place within it. This pursuit is not just academic, as cosmologists attempt to predict future cosmic events, ranging from the life cycles of stars to the catastrophic impact of asteroid collisions. They rely on an intricate combination of observational data, mathematical modeling, and sophisticated simulations. The behavior of celestial objects, such as the movement of planets, can be forecasted with remarkable precision using Kepler's laws of planetary motion, which describe the elliptical orbits of planets and other objects in space. By applying these laws, astronomers can not only predict the future positions of planets with impressive accuracy, but also anticipate the long-term behavior of star systems. In recent years, advancements in technology, especially through the use of high-powered telescopes and computational models, have enabled researchers to gather a vast amount of data from every corner of the universe. Observations of distant stars, galaxies, and supernovae, some of which are billions of light years away, have provided crucial insights into the universe's past, present, and future. The data collected from these observations are synthesized into models that give researchers a clearer picture of how cosmic events unfold, such as the death of stars, the behavior of black holes, and the formation and eventual destruction of galaxies. At the heart of these models is mathematics. Through complex equations, scientists approximate the behavior of celestial bodies and their interactions. With the help of supercomputers, they can simulate entire universes over vast timescales, visualizing the birth, evolution, and death of galaxies. These simulations are not mere speculative exercises. They are tools that allow cosmologists to test hypotheses about how galaxies evolve, merge, and transform under various cosmic conditions. For example, simulations can help predict the future merging of our Milky Way galaxy with the Andromeda galaxy, an event that will occur several billion years from now. But the universe is unpredictable, and not all factors can be accounted for. That's where probability and statistics come into play. While certain cosmic phenomena like planetary motion can be modeled with high precision, many events are influenced by numerous variables that are either unknown or too complex to measure with current technology. By assessing probabilities and modeling a range of possible scenarios, scientists can make more robust predictions about future events, such as the likelihood of an asteroid impact or the potential for a supernova explosion in a distant star system. This multidisciplinary approach, which combines observational data, mathematical modeling, and probability theory, has made great strides in enhancing our understanding of the cosmos. However, some of the most profound questions about the universe's origins remain unresolved. The Big Bang, the event that marks the beginning of space and time as we know it, is still a source of deep mystery. While it is generally accepted that the universe began as an infinitely small, dense point, often referred to as a singularity, what happened at that moment remains unclear. Our current understanding of the laws of physics breaks down under the extreme conditions present at the time of the Big Bang, creating a significant gap in our comprehension of the universe's earliest moments. This gap in knowledge has spurred ongoing research in fields like quantum gravity and string theory, which attempt to explain how the laws of physics might have operated under such extreme conditions. These theories may eventually provide the key to understanding how space and time themselves emerged from the primordial singularity, potentially offering answers to some of the universe's most fundamental questions. One promising theory that may hold the answer to the early conditions of the universe is the concept of cosmic inflation. This theory posits that just fractions of a second after the Big Bang, the universe underwent a rapid and exponential expansion, smoothing out irregularities and setting the stage for the large-scale structure we observe today. Understanding cosmic inflation is crucial for understanding the universe's birth. Scientists are currently investigating the physical mechanisms behind this inflationary period, trying to identify what forces were at work during this rapid expansion and whether an inflationary field might have driven it. Was there an interaction between this field and other components of the early universe, such as quantum fluctuations? Could these interactions explain the uniformity of the cosmos today, despite the vast distances between its most distant regions? These are some of the pressing questions that cosmologists are tackling as they strive to piece together the puzzle of the universe's early history. In this quest for knowledge, the diverse and evolving models of the universe reflect the adaptive nature of scientific inquiry. What was once considered speculative or fringe now stands at the forefront of cosmological research, challenging old paradigms and offering new perspectives on the universe's creation, evolution, and ultimate fate. The dynamic nature of science means that as we continue to explore and refine our models of the cosmos, each discovery, no matter how small, opens new doors, leading us deeper into the mystery of our existence. In recent years, investigations into the cosmic microwave background radiation, CMB, have offered us an invaluable snapshot of the universe at an astonishingly early stage, just 380,000 years after the Big Bang. This radiation, a faint afterglow of the Big Bang itself, serves as one of the most powerful tools for astronomers and physicists alike. Yet despite its significance, the CMB alone cannot provide the full story of the universe's birth. It offers only a partial glimpse, a faint echo of the cosmos's earliest moments. To uncover a more complete picture, researchers turn to a vast array of advanced instruments, including particle accelerators and large-scale telescopes, relentlessly searching for more precise measurements and novel data that may finally unravel the universe's deepest secrets. The quest for answers in this domain is nothing short of monumental. It is a pursuit that not only deepens our understanding of where the universe came from, but also illuminates the very fabric of reality itself. This ongoing journey to understand the cosmos involves a delicate dance between observational data and theoretical models, both of which are constantly evolving. Scientists begin by developing cosmological models grounded in established scientific principles and physical laws, such as Einstein's theory of general relativity. These models form the theoretical foundation, predicting the behavior and properties of the universe from its earliest moments to its current state. Once these models are in place, astronomers and physicists embark on a quest for observational data, utilizing cutting-edge technology. Telescopes, capable of observing a vast spectrum of wavelengths, from radio and infrared to visible light, help scientists peer deep into space. They collect a tremendous volume of data, each new observation providing fresh insights that either confirm or challenge existing models. When a model aligns well with the data, it bolsters the model's credibility. But when discrepancies arise, the scientific community is compelled to re-examine the assumptions underlying the model, refine existing theories, or in some cases, discard them entirely in favor of new ones. This iterative process, an ongoing cycle of observation, hypothesis, and refinement, ensures that our understanding of the universe adapts in step with new discoveries. An intriguing aspect of this scientific process is how researchers apply statistical methods to assess the validity of their models. For example, they may run simulations based on a given model and then compare the outcomes with actual observational data. If a model consistently fails to explain critical phenomena, such as the accelerated expansion of the universe, it becomes clear that either a new theory or adjustments to the current model are necessary. Through these rigorous comparisons, scientists gradually peel away layers of mystery, inching ever closer to the true nature of the cosmos. Yet this journey is not a solitary endeavor. The complexities of the universe are so vast that they demand collaboration across a variety of disciplines. Physicists, astronomers, cosmologists, and even computer scientists must work together, sharing insights and expertise to develop a more comprehensive understanding of the universe's workings. This collaboration fosters an environment where theories are constantly reassessed and revised based on fresh observational evidence. As a result, our collective understanding of the cosmos becomes more nuanced and sophisticated with each new contribution from different fields. The importance of interdisciplinary research cannot be overstated. Cosmology, which is the scientific study of the universe's origin, evolution, and eventual fate, draws on a wide range of fields, including physics, astronomy, mathematics, and even philosophy. By combining methodologies from each of these disciplines, researchers are able to address the multifaceted nature of cosmic phenomena in a more holistic way. For instance, breakthroughs in theoretical physics, especially in fields such as quantum mechanics and general relativity, have had profound implications for our understanding of the early universe. Collaborative efforts between particle physicists and cosmologists have led to groundbreaking theories such as cosmic inflation, which proposes that space expanded exponentially in the moments following the Big Bang. This interwoven synergy between disciplines allows for a more robust scientific framework, enabling scientists to test and refine their ideas in a comprehensive manner. Furthermore, the data collected by observatories equipped with state-of-the-art technology often require specialized knowledge in fields like engineering, computer science, and data analytics. Astronomers frequently collaborate with these experts to develop sophisticated algorithms and data processing tools capable of revealing patterns hidden within vast amounts of cosmic data. This collaborative, multidimensional approach not only advances our understanding of the universe, but also drives innovation within the fields that contribute to cosmology. In many ways, these collaborations have led to significant advances in technology, benefiting both scientific discovery and practical applications in other areas. Interdisciplinary research also opens doors to new avenues of inquiry. By fostering connections between seemingly unrelated fields, researchers are able to explore fresh questions and ideas. These breakthroughs, in turn, inspire new lines of investigation that push the boundaries of our knowledge and challenge our understanding of reality itself. As we continue our quest to unravel the mysteries of the universe, this collaborative spirit will remain essential to our success. Cultural beliefs also play an important role in shaping humanity's understanding of the cosmos. Throughout history, different cultures have developed unique mythologies, cosmologies, and philosophical frameworks to explain the nature of the universe and our place within it. In ancient civilizations, such as those of the Greeks and Babylonians, the stars and planets were often associated with gods and goddesses, reflecting the values and experiences of those societies. These mythological frameworks provided a way to make sense of the heavens, blending science with religious and cultural narratives. In contemporary society, cultural views of the universe continue to be influenced by specific value systems and traditions. For example, some indigenous cultures view the cosmos not as a distant, detached entity, but as a living, interconnected system. In these worldviews, there is a reciprocal relationship between humanity, nature, and the universe, a relationship that emphasizes harmony and mutual respect rather than dominance. This holistic perspective often shapes practices related to astronomy, agriculture, and environmental stewardship, reflecting a deep reverence for the natural world and a recognition of the intricate interconnectedness of all things. In conclusion, the pursuit of cosmic knowledge is a collective, multidisciplinary endeavor that bridges the gap between science and culture. As our understanding of the universe evolves, it is shaped by a dynamic interplay between observational data, theoretical models, and cultural perspectives. The continued collaboration between scientists from diverse fields will ultimately push the boundaries of our knowledge, uncovering new mysteries and shedding light on the very origins of our existence. As we look to the stars, we are not merely seeking answers about the cosmos. We are, in a very real sense, seeking to understand the deepest truths of our own place in the universe. The way scientific advancements are received by societies around the world can be deeply influenced by cultural interpretations. In societies where scientific reasoning is widely accepted and deeply integrated into everyday life, there is often a strong connection to groundbreaking theories that shape our understanding of the universe. Take, for example, the Big Bang Theory, or the concept of black holes, ideas that have transformed our comprehension of space and time. These concepts are embraced as part of a larger narrative that seeks to explain the origins and nature of the cosmos. However, in societies where traditional beliefs dominate, the reception of such scientific concepts may be more resistant. Ideas that challenge long-standing cultural narratives, even when backed by overwhelming evidence, can face opposition. This resistance arises from the tension between established beliefs and the disruptive nature of new scientific discoveries. Yet this interplay between cultural traditions and scientific progress is not static. It is a dynamic and ongoing process. It perpetually shapes humanity's collective quest for knowledge and understanding of the universe. As global communication expands and diverse perspectives converge, our shared understanding of the cosmos continues to evolve, revealing not only the profound mysteries of space, but also the deep influence that cultural narratives exert on how we perceive and interpret these discoveries. Space exploration plays a pivotal role in transforming society's view of humanity's place in the universe. Over the years, missions to the Moon, Mars, and beyond have expanded the frontiers of human knowledge and ignited a sense of wonder about our planet and the vastness of the cosmos. Iconic images, such as the Earthrise photograph taken during the Apollo 8 mission, have shifted the global perspective on our planet. They remind us of Earth's fragility and underscore the interconnectedness of all life on it. Such moments inspire people worldwide to reflect on our shared existence and the collective responsibility we have to protect our home. As we venture further into space, each new discovery challenges and refines our understanding of where we fit the cosmic narrative. The search for extraterrestrial life, for instance, raises fundamental philosophical and scientific questions. Are we alone in the universe? With the discovery of exoplanets located in habitable zones around distant stars, the possibility of life beyond Earth seems ever more plausible. These findings spark curiosity and prompt discussions about what such discoveries mean for humanity's future. They push us to reconsider not only the place of life in the universe, but also our role in the larger cosmic story. Moreover, space exploration has become a force of unity. It transcends national borders and fosters international collaboration. Projects like the International Space Station, ISS, are prime examples of how the global community can come together to achieve common goals. These efforts not only serve as scientific missions, but also as critical milestones in human achievement. Through these collaborations, diverse cultures are united, creating a shared identity as humans exploring the cosmos together. The advancement of technology and the expanding body of scientific knowledge continue to reshape societal perceptions. Every mission into space does more than just broaden our understanding of the universe. It captures the collective imagination. This ongoing journey sparks dreams and ambitions across generations, inspiring people to look toward the stars and ponder their place in an ever-expanding universe, full of mystery and potential. Educational initiatives play an essential role in making these cosmic mysteries accessible to the public. By presenting complex scientific concepts in engaging and understandable ways, these programs bring the wonders of space into the lives of many. Workshops, lectures, and interactive exhibits at science centers and planetariums are powerful tools in sparking curiosity. Through these platforms, educational organizations aim to ignite wonder about the universe, delving into topics like black holes, dark matter, and the origins of the cosmos. Schools and universities are crucial players in this effort as well. Many institutions now incorporate astronomy and cosmology into their curricula, offering students hands-on experiences with telescopes, simulations, and collaborative research projects. By fostering a learning environment that encourages exploration and critical thinking, educators are empowering a new generation with the knowledge and curiosity needed to understand the vastness of space and its profound mysteries. In addition, initiatives that reach the public through social media and digital platforms are becoming increasingly popular. These resources allow experts to share their discoveries and insights with a global audience, democratizing access to scientific knowledge. With the rise of online content such as thought-provoking interviews, documentaries, and live-streamed lectures, people can engage with scientific ideas and discussions in real time. These digital spaces spark curiosity and generate interest in cosmic phenomena, providing a platform for ongoing dialogue and exploration. In this interconnected world, the pursuit of space exploration, fueled by scientific innovation and cultural collaboration, will continue to shape our understanding of the universe. As we push the boundaries of what is known and challenge our perceptions, we stand on the precipice of even greater discoveries, ready to unlock the mysteries of the cosmos and better understand our place within it. Community events such as science fairs, star parties, and astronomy clubs play a pivotal role in fostering a sense of collective exploration and discovery. These gatherings serve as a vibrant meeting point for individuals to share experiences, insights, and findings, ultimately deepening the public's connection with the universe. By combining education with collaboration, these initiatives not only raise awareness, but also nurture a shared appreciation for the cosmic mysteries that continue to captivate the human spirit. When people come together in this way, they are united by a common fascination with the cosmos, and this collective engagement can have profound effects on society's relationship with space. Public engagement is a cornerstone in the advancement of space research and exploration. Through initiatives that raise awareness, spark interest, and galvanize support for scientific endeavors, communities become advocates for space missions and policies. When the public is well-informed and actively involved, they are more likely to rally behind funding and legislative action that prioritize space exploration. In this way, public engagement does more than simply inform. It builds a foundation of support that fuels future scientific breakthroughs and missions. The impact of engaging the public cannot be overstated, particularly in its ability to inspire the next generation of scientists and explorers. Science, technology, engineering, and mathematics, STEM fields, are critical to the future of space exploration, and engaging the public early on helps cultivate interest in these disciplines. Educational outreach programs play a crucial role in this, offering young people a glimpse into the vast possibilities that lie in careers related to space sciences. A passionate and informed public can spark the curiosity and drive of young minds, preparing them to tackle the challenges and innovations of tomorrow. Moreover, public engagement allows scientists to communicate their discoveries and objectives with greater clarity and impact. When researchers share the results of their work, whether it's exploring distant planets, conducting asteroid missions, or investigating the potential for extraterrestrial life, the narrative extends beyond the scientific community. These stories capture the public's imagination, making the abstract tangible and fueling support for ambitious endeavors like sending humans to Mars or establishing a permanent presence on the moon. The power of these stories lies in their ability to inspire and unify the public, turning what were once distant dreams into achievable goals. Fascination with space can translate into real-world support for space agencies and private companies dedicated to advancing space technology. NASA, private aerospace firms, and research institutions all rely on the enthusiasm and advocacy of the public to secure funding and resources for their projects. The more people understand and feel connected to the goals of space exploration, the more likely they are to back initiatives that push the boundaries of human knowledge and capability. Listening to the public's perspective also adds value to the direction of research. Different communities have unique concerns and interests when it comes to space exploration, from planetary defense against asteroids, to the ethical implications of colonizing other planets. Public engagement allows researchers to tap into these diverse viewpoints, providing them with invaluable insights that can guide the development of programs that reflect the values and priorities of society as a whole. By embracing these contributions, space exploration becomes a shared journey, one that involves a collective effort rather than a solitary, isolated pursuit. In addition, public engagement helps demystify science, creating open lines of communication between scientists and the general public. Misconceptions about space exploration, space technology, and the scientific method are often rooted in a lack of understanding. By addressing these misunderstandings through clear, accessible dialogue, trust can be built between the scientific community and the public. As people gain a better understanding of the processes behind scientific discovery, they are more likely to support policies that promote further space exploration and investment in research. The more the public is engaged, the more they contribute to a broader culture that values scientific inquiry, which in turn propels humanity further into the cosmos. The portrayal of space in media and literature has long shaped public interest in astronomy and space exploration. For generations, books, films, and television shows have captured the collective imagination of audiences, often blending scientific concepts with human drama and adventure. Iconic works like Jules Verne's From the Earth to the Moon, and more recent films like Interstellar and The Martian have not only entertained but also piqued curiosity about the cosmos. These stories introduce viewers to complex astronomical ideas in ways that are accessible and engaging, turning abstract concepts into thrilling, real-world possibilities. The marriage of storytelling and science has played a key role in making space exploration not just an academic subject, but a source of inspiration. These portrayals have a powerful effect on audiences, creating a sense of wonder about the universe and our place within it. When characters embark on daring journeys to distant planets or wrestle with the mysteries of black holes, viewers are invited to think beyond the confines of Earth and imagine what lies beyond. These stories frequently stir a desire for deeper knowledge about space exploration, astrobiology, and even theoretical physics, encouraging audiences to seek out real scientific information on these topics. As a result, media representations of space serve as a gateway to further interest in the field of astronomy, sparking the curiosity of people who might otherwise have never thought to look up at the night sky and wonder about the mysteries it holds. Ultimately, the blend of public engagement, scientific communication, and the power of storytelling creates a dynamic environment where space exploration is not merely a field of study, but a shared human adventure. With increased public support, education, and a sense of collective wonder, humanity is poised to continue its quest to explore the stars and unlock the secrets of the universe. Astronomy, a discipline that has intrigued and captivated humanity for millennia, has become a vibrant and deeply influential force in modern society. Through the compelling narratives of educational programs, documentaries, and media coverage, the stars and planets are no longer distant objects of wonder, but are integrated into the cultural fabric of everyday life. These programs, rich in stunning visuals and engaging storytelling, spark curiosity in broad audiences, making astronomical phenomena feel tangible, exciting, and even approachable. When astronomical events, such as a rare solar eclipse or an alignment of planets, are broadcast on popular channels, there is often a noticeable surge in viewership and public interest. The images and information presented make these cosmic occurrences feel relevant to everyone, drawing people from all walks of life to look up at the sky with awe and wonder. It is not just the immediate impact of these visual portrayals that matters, but the long-term effects they have on the public's perception of the universe. As more and more people tune in to learn about these celestial events, there is a natural increase in curiosity and engagement with the broader field of astronomy. This growing public interest can have a significant ripple effect, including an increase in funding for scientific research and educational initiatives in the field. Media portrayals, from documentaries to fictional films, also play a pivotal role in inspiring the next generation of scientists and astronomers. For many young viewers, the images and stories they encounter through the media ignite a spark of curiosity and ambition, motivating them to pursue careers in space exploration, astrophysics, and related fields. Children who watch a documentary on distant planets or the search for extraterrestrial life often dream of gazing through telescopes and contributing to the quest for understanding the universe's mysteries. Thus, the relationship between the media and public engagement with astronomy is profound, serving as a vital bridge between imagination and scientific reality. Through the lens of media portrayals, the universe comes alive, not just as a vast, impersonal expanse, but as a source of endless possibilities and scientific inquiry. But the engagement doesn't stop at simply watching. It evolves into active participation in scientific endeavors. The advent of citizen science has transformed how we understand the cosmos by inviting the public to become contributors to scientific research. Ordinary individuals, regardless of their background or expertise, are now empowered to play an active role in astronomical discoveries and in turn expand our collective understanding of the universe. Citizen science enables people to engage with scientific research in ways that were previously unthinkable. From tracking the movements of comets to classifying galaxies, these volunteers are essential in helping professionals process massive amounts of data. In doing so, they significantly lighten the load for scientists, allowing them to focus on complex analyses while citizens contribute to gathering raw data. The impact of this collaboration has been nothing short of groundbreaking. Amateurs with access to affordable telescopes and software have assisted in discovering new celestial bodies, like asteroids and comets. Moreover, their observations provide crucial information on phenomena such as variable stars and light curves, which can offer insights into the behavior of distant galaxies. One of the most prominent examples of the power of citizen science is projects like Galaxy Zoo, which invites volunteers to classify millions of galaxy images. In this collaborative effort, the public plays a critical role in discovering previously unnoticed features, such as unusual galaxy shapes and unexpected cosmic formations. These discoveries are important because they challenge existing scientific theories and open new avenues of exploration. While algorithms can process vast amounts of data quickly, human participants are often better at spotting patterns, outliers, and anomalies, small details that could otherwise be missed. In this sense, the work of volunteers enriches the scientific process, providing insights into the formation and evolution of the universe. The value of citizen science also extends beyond observational data. In more theoretical realms, individuals can engage with research that involves complex simulations of cosmic events or participate in the analysis of data from highly specialized projects, such as the Laser Interferometer Gravitational Wave Observatory, LIGO. These opportunities allow everyday people to contribute to some of the most cutting-edge research in physics and astronomy, extending the intellectual reach of scientific communities while fostering a deeper public interest in these fields. In turn, this collaboration enhances our collective comprehension of the cosmos and reaffirms the importance of public involvement in scientific progress. Throughout history, celestial phenomena have been sources of inspiration, wonder, and reverence across diverse cultures. Ancient civilizations like the Babylonians carefully tracked the movements of planets, seeing them as powerful omens that could predict the outcomes of battles or the fate of harvests. For them, the heavens were not just a backdrop to human existence, but an active force that shaped their understanding of fate, fortune, and divine will. The alignment of stars and planets was believed to be a divine message, offering guidance on important matters of life. In contrast, many indigenous cultures also look to the skies, but with a distinct worldview. For example, the Inuit of the Arctic regions interpreted the northern lights as the spirits of their ancestors dancing in the sky. These celestial phenomena were not merely myths or stories. They were deeply integrated into the cultural and spiritual identity of the people. The northern lights served as a point of connection with the past, guiding their navigation, influencing storytelling, and playing a role in seasonal ceremonies. Through these stories, the movement of stars and celestial bodies was a profound way of maintaining ties to the world beyond the immediate and the tangible. These cultural interpretations of celestial events highlight the diversity of human engagement with the universe. While some saw the stars as divine indicators, others viewed them as guides to a deeper understanding of human existence and spirituality. What is clear, however, is that the stars have always been a source of fascination and reflection, inspiring generations to look beyond themselves and ponder the mysteries of the cosmos. In the modern era, media continues to keep this fascination alive, blending the wonder of the stars with the science that helps us understand them. Documentaries and educational programming, through their breathtaking visuals and captivating narratives, fuel our collective curiosity. They create a culture of inquiry, where people are inspired not just to gaze at the stars, but to question their significance, and in doing so, engage with the ongoing exploration of the universe. The legacy of human interest in the stars is no longer just about mythical interpretations, but about connecting to the vastness of space itself, both scientifically and imaginatively. Through this union of media, education, and citizen science, we can continue to explore the universe and discover new truths about our place in it. Asian cultures have developed their own unique ways of interpreting the cosmos, offering deep insights into their societal values and beliefs. In Chinese astronomy, the movement of celestial bodies was not merely seen as a physical phenomenon, but as an intricate reflection of the moral conduct of rulers. A comet, for example, might be viewed not just as an astronomical event, but as an omen, a celestial warning suggesting that a shift in leadership or a change in political direction was imminent. This connection between the heavens and the rulers' actions underscores the idea that what happens in the sky can deeply influence what happens on Earth. Such interpretations reveal more than just diverse cultural beliefs. They speak to a shared human desire to understand our place in the universe. Whether in China, Europe, or the Americas, people have looked to the stars not just for scientific knowledge, but for guidance on how to live their lives and govern their societies. These celestial events, often seen through the lens of omens, ancestral connections, or even moral indicators, show how humanity's link to the cosmos has shaped societies across time and space. Even though interpretations differ from culture to culture, they unite us in our longing to grasp something greater than ourselves, the mystery of the universe and our place within it. The fact that so many cultures have looked to the sky for meaning and guidance reveals a fundamental human trait: our shared desire to find purpose and direction in a vast and often unfathomable cosmos. This connection between celestial phenomena and human existence continues to captivate us. The fascination with the stars, planets, and other cosmic occurrences is not just about understanding the physical world. It's about seeking a deeper meaning that can help us navigate the complexities of life on Earth. The appearance of unusual events in the sky, like eclipses or comets, continues to inspire awe, wonder, and even fear. These cosmic occurrences have always been seen as more than just random events. They are viewed as clues guiding humanity in its eternal quest for meaning and understanding. Moving from cultural interpretations to a more contemporary focus, the search for extraterrestrial intelligence, SETI, serves as a modern reflection of humanity's deepest desires and fears. At its core, SETI represents our longing to connect with something beyond our planet, the hope that we are not alone in the universe. This search is driven by an insatiable curiosity, fueled by questions that have persisted for centuries. Are we the only intelligent beings in this vast cosmos, or is there life elsewhere? The desire to discover extraterrestrial intelligence isn't just about curiosity. It also represents an existential contemplation. The idea of finding other intelligent life offers us not just a potential confirmation of our own significance, but also the thrilling possibility of engaging with other civilizations. Imagine sharing knowledge, culture, and technology with beings from distant worlds, a concept that stirs both excitement and fear. This mix of hope and anxiety encapsulates the human experience, as we simultaneously yearn for connection and worry about the potential risks that such an encounter could bring. Yet this quest is not without its darker undertones. The discovery of extraterrestrial civilizations raises questions that delve into the very essence of humanity. Will these beings be benevolent, indifferent, or hostile? Science fiction often explores these fears, imagining scenarios where contact with extraterrestrials either leads to uplifting collaboration or catastrophic consequences. These stories tap into a primal anxiety about our vulnerability and our ability to handle the unknown. They reflect a fear that if we are not careful, we might invite harm or disruption into our world. Moreover, the search for extraterrestrial intelligence also mirrors humanity's deeper fears of isolation. If we were to discover that intelligent life exists elsewhere, it might challenge our sense of self-importance. The realization that we are just one of many civilizations in the universe could prompt a humbling reflection on the fragility of human existence. Are we really as special as we like to believe? Or are we simply one small, fleeting civilization among countless others that rise and fall over the course of cosmic time? Such a realization could evoke a deep sense of impermanence, reminding us of our relative insignificance in the grand scheme of the universe. In addition to these existential questions, the pursuit of SETI also reflects a philosophical inquiry into the nature of life itself. By asking whether life exists elsewhere, we are simultaneously exploring what it means to be alive. What defines intelligence? What does it mean to be human? These questions don't just have implications for the search for life in space, they also have profound consequences for how we understand ourselves on Earth. As we search for answers beyond our planet, we are also seeking to better understand the nature of our own existence. This investigation also brings with it the potential for tremendous technological and cultural advancements. The possibility of contacting extraterrestrial civilizations raises the exciting prospect of shared knowledge, wisdom, and technological progress. Imagine the discoveries that could come from interacting with a more advanced civilization. Breakthroughs in energy, medicine, and perhaps even the fundamental laws of physics. Yet, this same desire for progress is tempered by concern. What if the encounter does not go as hoped? What if such contact leads to unforeseen dangers? As this search continues, it sparks a broader conversation about our place in the universe and the nature of our existence. The tension between our hopes and fears fuels this ongoing exploration, inviting us to reflect on who we are and where we are headed. The search for extraterrestrial intelligence isn't just a scientific endeavor. It's a mirror of our deepest questions, our hopes, and our anxieties. Interdisciplinary collaborations have become crucial in advancing our understanding of the cosmos. The integration of expertise from various fields, such as physics, astronomy, biology, and even philosophy, creates a vibrant and dynamic environment for tackling the complex questions that arise in the study of the universe. For instance, astrophysics relies heavily on the insights provided by mathematics and computer science. These fields help model cosmic events and simulate galaxy formations, giving us deeper insight into the mechanics of the universe. Moreover, the collaboration between astronomers and chemists has yielded groundbreaking discoveries about the chemical processes occurring in stars and other celestial bodies. Understanding the composition of stars and the formation of molecules in space not only advances our knowledge of the universe, but also has practical applications for fields like astrobiology. Knowing which chemical compounds are essential for life can help us identify potential life-sustaining environments beyond Earth, guiding future missions to planets and moons where life might exist. These interdisciplinary collaborations are reshaping our understanding of the universe, offering new ways to address long-standing scientific questions. By combining insights from different scientific fields, we are able to create a more comprehensive and nuanced picture of the cosmos. This collective effort underscores the interconnectedness of knowledge, highlighting how collaboration across disciplines can drive progress and innovation in the search for answers to some of humanity's most profound questions. Furthermore, interdisciplinary collaboration has the power to disrupt traditional scientific paradigms, pushing researchers to think beyond the limitations of their individual fields. By combining knowledge from various disciplines, new ideas emerge that were once considered improbable or even impossible. Take, for instance, the investigation into the potential for life beyond Earth. This pursuit doesn't rest solely on the shoulders of astronomers. It requires an intricate blend of geology, biology, and atmospheric science. Geologists provide insights into the conditions necessary for life to thrive. Biologists explore the adaptability of organisms to extreme environments. And atmospheric scientists study the potential for habitable atmospheres on distant planets. By working together, these disciplines offer a comprehensive approach to understanding life's potential across the cosmos. Such collaborations are vital as technological advancements continue to accelerate. Sophisticated tools like high-powered telescopes, advanced satellite instruments, and cutting-edge data analysis software necessitate expertise from diverse scientific fields. The synergy between engineers, physicists, and data scientists is crucial to not just collecting vast amounts of data, but interpreting it accurately. Every breakthrough, whether in space exploration or the development of new technologies, is increasingly rooted in interdisciplinary teamwork. Without it, many of our most ambitious scientific endeavors would remain out of reach. The search for extraterrestrial life in particular raises a host of ethical dilemmas. One of the most pressing concerns is whether humanity has the right to explore and potentially alter environments inhabited by alien organisms. This is not just a theoretical question, it's one that mirrors our own conservation efforts on Earth. Much like how we strive to protect endangered species and fragile ecosystems on our planet, similar principles could guide our interaction with other worlds. Some argue that we should extend these ethical considerations to extraterrestrial ecosystems, ensuring that we do not disrupt or destroy potential habitats. Ethics also come into play when we consider the rights of intelligent extraterrestrial beings. If we were to discover alien life forms that exhibit advanced intelligence or social structures, it would challenge our fundamental understanding of autonomy and moral responsibility. Questions would arise. Do these beings have a right to their own existence? Would we have an obligation to communicate with them, share knowledge, or even intervene to help ensure their survival? Such considerations push the boundaries of how we define sentient beings and the moral obligations that come with that designation. In addition to the moral questions surrounding extraterrestrial life, the discovery of intelligent beings could dramatically shift humanity's worldview. The idea that we are not alone in the universe has the potential to both unite and divide humanity. On one hand, it could foster a sense of global unity, like as we come together to share knowledge and resources in the pursuit of a greater understanding of the cosmos. On the other hand, it could spark fear, territorialism, and conflict as nations and groups vie for control over new discoveries and the potential power they represent. The social and political ramifications of such a discovery would be profound and could redefine our place in the universe. This intersection of technology, ethics, and cosmology becomes even more important as we develop the tools needed to explore the universe. The current methods for detecting and studying extraterrestrial life are still in their infancy. There are concerns, for instance, about contamination, both the risk of introducing Earth organisms into alien environments and the reverse, the potential for alien microbes to contaminate our planet. To address these concerns, strict protocols must be established to govern space exploration. These measures should ensure that our search for life beyond Earth does not cause irreversible harm to extraterrestrial ecosystems. The balance between scientific curiosity and moral responsibility is delicate. As humanity reaches further into space, the pursuit of knowledge must always be tempered by an awareness of the consequences of our actions. This is especially true when considering the vast unknowns that lie ahead in the exploration of distant worlds. Each new discovery in cosmology has the potential to fundamentally alter our understanding of the universe. New findings often expose complexities that challenge long-held scientific beliefs. The detection of gravitational waves in 2015, for example, not only confirmed a critical prediction of Albert Einstein's theory of general relativity, but also unlocked an entirely new field of study: gravitational wave astronomy. This discovery has allowed scientists to observe the universe in ways that were previously unimaginable, offering a fresh perspective on some of the most fundamental forces in nature. Similarly, the discovery of dark energy has transformed our understanding of cosmic expansion. Initially, scientists believed that the universe's expansion was slowing due to gravitational forces. However, evidence now suggests that this expansion is accelerating, driven by a mysterious force known as dark energy. This revelation has forced scientists to re-examine our understanding of the universe's structure and its future, giving rise to numerous theories and ongoing investigations. Advancements in technology also play a critical role in reshaping our understanding of the cosmos. Powerful telescopes and increasingly sophisticated data analysis techniques allow astronomers to peer deeper into space, gathering unprecedented information about distant galaxies, black holes, and exoplanets. Each new discovery often leads to more questions than answers, pushing the boundaries of what we know. For example, the detection of potentially habitable exoplanets raises significant questions about the conditions necessary for life beyond Earth, and challenges our assumptions about what makes a planet suitable for life. As these discoveries accumulate, they create a more detailed and nuanced understanding of the universe. This evolving cosmic narrative is a direct result of interdisciplinary research, where physics, astronomy, and even philosophy intersect. Each breakthrough in one field leads to new insights and challenges in others, creating a cycle of knowledge that drives further exploration. However, the path forward is not without its obstacles. One of the greatest challenges in cosmology today is the nature of dark matter and dark energy. Together, these two phenomena constitute about 95% of the universe's total mass and energy, yet we are unable to directly observe them. This mystery lies at the heart of modern astrophysical research and has proven to be a significant roadblock in our understanding of the cosmos. In addition to these enigmatic substances, another critical challenge is the advancement of observational technologies. Both ground-based and space-based telescopes are essential for exploring the universe, yet current technology is limited in terms of sensitivity and resolution. Future telescopes must be able to detect fainter signals and provide more detailed images of distant celestial objects. Moreover, new technologies will be required to study high-energy cosmic events, which could offer vital clues about the evolution of the universe and the fundamental laws of physics. The quest for a unified theory of physics remains one of the most elusive goals in science. General relativity, which describes gravity, and quantum mechanics, which explains the behavior of subatomic particles, currently exist as separate frameworks. Finding a way to merge these two theories into a single cohesive model could revolutionize our understanding not only of the universe, but of the very nature of reality itself. As we continue to explore the cosmos, these challenges will undoubtedly push the limits of our scientific and technological capabilities. But they also present unparalleled opportunities for discovery, urging us to question the boundaries of our knowledge and expand our understanding of the universe in ways we can scarcely imagine. The need for international collaboration in addressing the immense challenges posed by the cosmos is more crucial than ever. The complexity of the universe requires that knowledge, resources, and expertise be shared across borders. Only through uniting scientists from diverse backgrounds and disciplines can we foster innovation and create pathways to breakthroughs that may one day transform our understanding of the universe itself. By embracing a collaborative spirit, humanity can venture further into the unknown, unlocking secrets that have long eluded our grasp. This is the power of unity, a collective endeavor that propels us toward discoveries beyond our wildest imaginations. The quest to understand the universe has always sparked curiosity and imagination. It serves as a beacon, guiding future generations of scientists, thinkers, and dreamers toward new frontiers. From the vast expanses of dark matter to the intricate dance of celestial bodies, today's discoveries reveal the profound interconnectedness of everything that exists. These monumental findings not only challenge our understanding of the cosmos, but also inspire critical thinking and problem solving. As young minds are encouraged to ask questions and seek answers about the nature of reality, they participate in an ongoing dialogue that stretches across generations. When students dive into concepts like quantum mechanics, relativity, and the nature of space-time, they are not merely absorbing dry facts. They are engaging in a grand intellectual tradition, one that has been shaped by the likes of Albert Einstein, Marie Curie, Carl Sagan, and many others. These legendary scientists serve as role models, reminding young individuals that their own potential contributions to the field are limitless. Recognizing the universe as a dynamic and ever-changing entity, full of mysteries waiting to be unraveled, can ignite a passion that drives students toward careers in science, technology, engineering, and mathematics, STEM. In this way, the exploration of the cosmos does not only contribute to human knowledge, but also shapes the future workforce of the scientific community. Moreover, science communication initiatives and hands-on programs in observatories and laboratories play a pivotal role in making complex ideas more accessible to the public. When students can see firsthand how cosmic phenomena align with practical real-world experience, they gain a deeper understanding of the tangible impact their work can have. Through interactive demonstrations, experiments, and even virtual reality simulations, budding scientists are transported into the depths of space. These immersive experiences provide a visceral understanding of concepts that often feel abstract, making the mysteries of the universe feel just within reach. Ultimately, the pursuit of cosmic knowledge does more than expand our intellectual horizons. It reshapes the way we view our place in the universe. As future scientists confront questions that stretch the limits of human understanding, their intellectual journeys will not only shape their minds, but also instill a profound sense of wonder and responsibility toward the world they inhabit. With the knowledge gained from their cosmic explorations, these individuals will be better equipped to address the pressing challenges facing humanity today, potentially leading to groundbreaking innovations inspired by the very mysteries of the universe. Collaboration among international space agencies plays an indispensable role in advancing cosmic research. The vast and often insurmountable challenges of space exploration are far too great for any single nation to tackle alone. By pooling resources, expertise, and technology, space agencies can pursue shared goals and amplify the impact of their work. Agencies like NASA, the European Space Agency, ESA, and Roscosmos have recognized this reality, forming collaborative partnerships that benefit not only their respective countries, but all of humanity. One of the most prominent examples of such cooperation is the International Space Station, ISS, a platform where scientists from around the world work together to conduct experiments that provide valuable insights into everything from biology to physics. The sharing of data and discoveries across borders accelerates the pace of research, leading to more comprehensive studies of the cosmos. For instance, the Hubble Space Telescope, a joint project among various countries, has provided groundbreaking images and data that have transformed our understanding of the universe. By pooling observational data and combining the capabilities of different instruments, space agencies can examine complex phenomena such as black holes, dark matter, and cosmic radiation in ways that would be impossible for any single country to achieve on its own. This collaborative effort not only enhances our knowledge of the universe, but also pushes the boundaries of scientific exploration. Furthermore, international collaboration fosters innovation in ways that extend beyond the realm of space exploration. When teams from different countries and cultures come together to solve complex problems, they bring unique perspectives and approaches that can lead to technological advancements with far-reaching applications. For example, the technologies developed for space missions have been adapted for use in other fields, such as medicine, telecommunications, and even disaster response. These cross-pollinations of ideas demonstrate the broader impact of scientific cooperation, highlighting the far-reaching benefits that collaboration in space research can have on Earth. In conclusion, the future of cosmic research depends not only on individual nations' efforts, but also on a shared global commitment to collaboration. As we continue to unlock the mysteries of the universe, The combined efforts of scientists from around the world will be the driving force behind the next great leap in our understanding of space, time, and everything in between. Through collaboration, innovation, and the exchange of knowledge, humanity will move closer to answering the profound questions that have inspired generations of thinkers, opening new doors to the vast and mysterious universe that surrounds us. International collaboration in space has become a driving force for global unity, offering nations a platform to transcend borders and join together in the pursuit of a shared dream, the exploration of the cosmos. As countries collaborate, they forge not just scientific partnerships, but also strong bonds of trust, understanding, and mutual respect. Through space exploration, humanity shows its commitment to tackling challenges that transcend national interests, issues like climate change, resource scarcity, and the looming threat of asteroids. These concerns affect the entire planet, and the need for a collective response has never been more urgent. In a world that seems increasingly divided, the cooperation among space agencies stands as a powerful reminder of what humanity can achieve when united in the spirit of discovery. As we deepen our understanding of the universe, our relationship with the cosmos undergoes a profound transformation. Every new discovery, from the detection of distant exoplanets to the mysterious phenomena of black holes, brings us closer to unraveling the vast mysteries that surround us. With each breakthrough, our curiosity is satisfied, but more importantly, we begin to comprehend our place in the grand scheme of existence. This expanding knowledge reshapes not just our intellectual understanding, but our very sense of belonging within the universe. The more we learn, the more we realize how interconnected we are with the forces that govern the cosmos, highlighting the fragility and significance of our own existence. The role of technology in this transformation cannot be overstated. The progression of advanced telescopes and space exploration vehicles has radically expanded our ability to peer deeper into the universe. These innovations are not just technical feats, they are gateways to new realms of possibility. As we push further into space, we unlock the potential for groundbreaking new forms of communication and cooperation with other civilizations, should they exist. The dream of a universal community, united by a shared experience of existence, is no longer a mere fantasy. It is slowly becoming a tangible reality, driven by the potential to learn from civilizations beyond our own planet. Moreover, as we continue to probe the enigma of dark matter and dark energy, forces that shape the very fabric of the universe, we are also confronted with profound philosophical and ethical questions. What is the purpose of life? How do we ensure the sustainability of our planet in the face of escalating challenges? What does the future of human evolution look like in an ever-expanding universe? These are questions that have been pondered for millennia, but space exploration invites us to approach them with new perspectives. The answers may redefine our understanding of who we are and what we are capable of as a species. In this context, humanity's growing unity may not just be a metaphor, it could be a necessity. As we venture into space, we begin to recognize the urgent need for stewardship, not just of Earth, but of the cosmos itself. The responsibility to protect our planet and preserve the future of life on Earth could become inextricably linked to our efforts to explore and utilize outer space. Our explorations may help us understand how to safeguard our home while extending the reach of human civilization across the stars. At the same time, this expanding knowledge of space opens the door to a future where we can harness cosmic resources in ways that were once the stuff of science fiction. From asteroid mining to capturing the immense energy of the sun, these possibilities have the potential to revolutionize industries and societies on Earth. Imagine a future where space is not just a destination, but a source of sustenance and growth. The notion of venturing beyond Earth may shift from an ambitious dream to a regular part of human life, with colonies on other planets or moons becoming as commonplace as international travel is today. This journey into the cosmos holds the promise not just of survival, but of flourishing. As humanity steps into the future, our potential to become an interstellar species, capable of thriving beyond the confines of Earth, becomes more tangible than ever. What it means to be human, and what our place in the universe truly is bound to change in ways we are only beginning to imagine. And as we continue this journey, we may find that the true measure of our progress is not just in our technological achievements, but in our ability to grow together as one species, united by the wonder and possibility that the cosmos offers.